Before time, before space, there was nothing. Absolute silence, endless darkness. But somehow, impossibly, existence burst forth, igniting reality itself. Like a sudden spark in a vast, empty void, our universe exploded into being. Scientists grappled to explain this cosmic miracle, proposing astonishing theories of spontaneous creation, quantum fluctuations, and realities beyond imagination. Yet, at the heart remains one haunting, unanswerable question. How can something truly emerge from nothing? Absolute nothing is a concept that challenges our understanding of reality. It refers to the complete absence of everything, not just matter and energy, but also space, time, and even the laws of physics themselves. This state of absolute nothingness is difficult for us to comprehend because our minds are accustomed to thinking in terms of something rather than nothing. In our universe, we observe that empty space is not truly empty. Quantum physics reveals that the vacuum of space is teeming with virtual particles that pop in and out of existence. These particles contribute to what scientists call vacuum energy or zero-point energy. Even in the coldest, darkest regions of space, this quantum activity persists. Absolute nothing goes beyond this quantum vacuum. It represents a state where even the fabric of space-time and the fundamental forces of nature do not exist. This concept is so foreign to our experience that it borders on the philosophical. Some physicists argue that absolute nothing may be inherently unstable, inevitably giving rise to something. The idea of absolute nothing plays a role in cosmological theories about the origin of our universe. Some propose that our cosmos emerged from such a state of nothingness, though the mechanisms for this emergence remain a subject of intense scientific inquiry and debate. Nothingness in physics is a concept far more complex than simply the absence of matter. Physicists grapple with defining true nothingness, as even the vacuum of space is not entirely empty. In quantum physics, the vacuum state is teeming with activity, filled with fluctuating quantum fields and virtual particles that pop in and out of existence. These quantum fluctuations are a fundamental aspect of the universe, occurring even in the absence of observable particles. The Heisenberg uncertainty principle suggests that true emptiness is impossible, as energy and time are intrinsically linked, allowing for the brief appearance of particle-antiparticle pairs. Furthermore, the concept of fields in physics complicates the notion of nothingness. Gravitational fields, electromagnetic fields, and other fundamental forces permeate space, making it challenging to conceive of a region entirely devoid of physical properties or influence. Ultimately, physicists define nothingness not as a complete void, but as the lowest possible energy state of the quantum vacuum. This state, while appearing empty to us, is actually a dynamic system full of potential, highlighting the profound interconnectedness of energy, matter, and space in our universe. The concept of true nothingness challenges the very foundations of human perception and cognition. Our brains have evolved to process and interpret sensory information from the world around us, making it extraordinarily difficult to conceptualize the absence of everything. When we attempt to imagine nothingness, we often visualize a dark, empty space. However, this mental image still contains elements such as space and time, which are not present in true nothingness. Even in the darkest, quietest environments, our minds generate internal stimuli, making it nearly impossible to experience complete sensory deprivation. From a philosophical and scientific standpoint, true nothingness goes beyond the absence of matter and energy. It implies the non-existence of space, time, and even the laws of physics themselves. This concept is so far removed from our everyday experiences that our brains struggle to create an accurate mental representation. Interestingly, some meditation practices aim to achieve states of mental emptiness, but even these experiences do not truly capture the essence of absolute nothingness. While humans can contemplate the idea of nothingness intellectually, Truly comprehending it in its purest form remains elusive, highlighting the limitations of our cognitive abilities when faced with concepts that exist outside the realm of our physical reality. The concept of absolute nothingness challenges our fundamental understanding of existence and reality. It forces us to confront the limits of human comprehension and the nature of being itself. Philosophers have long grappled with this idea, pondering whether true nothingness can exist or if it is merely a theoretical construct beyond our ability to fully grasp. One profound implication is the question of why there is something rather than nothing. If absolute nothingness were the default state of reality, then the existence of our universe becomes even more perplexing. This leads to discussions about the origins of existence and whether there must be some fundamental principle or force that prevents absolute nothingness from persisting. The concept also raises questions about consciousness and perception. If absolute nothingness existed, would it be possible to perceive or experience it? Some argue that the very act of observation or thought would introduce something into nothingness, making it impossible to truly encounter or understand. Furthermore, the idea of absolute nothingness challenges our notions of time and space. In a state of true nothingness, would these fundamental aspects of our reality exist? This thought experiment pushes us to reconsider the nature of reality itself and the boundaries of what we consider possible or meaningful in our quest to understand the cosmos. The concept of nothingness has fascinated humans for millennia, evolving from ancient philosophical musings to modern scientific theories. Early Greek philosophers grappled with the idea of a void, with some arguing it was impossible, while others saw it as a fundamental aspect of reality. Aristotle famously declared that nature abhors a vacuum, a belief that persisted for centuries. During the Middle Ages, the concept of nothingness took on religious overtones. Christian theologians debated whether God created the universe from absolute nothingness or if there was some pre-existing substance. This period saw nothingness often associated with non-existence and the absence of God. The scientific revolution brought new perspectives on nothingness. The development of vacuum pumps in the 17th century allowed scientists to create near-empty spaces, challenging long-held beliefs about the impossibility of a void. This led to a reimagining of nothingness as something that could be experimentally explored and measured. In modern physics, the concept of nothingness has taken on new dimensions. Quantum mechanics suggests that even in a vacuum, virtual particles constantly pop in and out of existence. This quantum foam challenges our understanding of emptiness, suggesting that true nothingness might be impossible in our universe. Today, scientists continue to explore the nature of vacuum energy and its implications for our understanding of the cosmos, showing that the concept of nothingness remains a rich area of inquiry in both philosophy and science. In our observable universe, true nothingness is an elusive concept. Even the vast expanses between galaxies, often thought of as empty space, are not truly devoid of everything. These cosmic voids contain trace amounts of matter, including hydrogen atoms, and are permeated by various fields, such as gravitational and electromagnetic fields. The closest approximation to nothingness we can observe is in the vacuum of space. However, even this vacuum is not entirely empty. Quantum mechanics tells us that the vacuum is teeming with virtual particles that constantly pop in and out of existence. These particles, though short-lived, contribute to what scientists call quantum vacuum fluctuations. Interestingly, the search for nothingness has led scientists to create artificial vacuums in laboratories. These are among the emptiest spaces known to us, yet they still contain trace amounts of matter and energy. The pursuit of absolute nothingness continues to challenge our understanding of physics and the nature of our universe. While true nothingness may not exist in our observable universe, the concept itself plays a crucial role in scientific theories, particularly in discussions about the origin of the universe and the nature of space-time. The quest to understand nothingness drives us to explore the fundamental fabric of reality itself. Quantum mechanics fundamentally reshapes our concept of nothingness, revealing a universe far stranger than classical physics ever suggested. In the quantum realm, true emptiness does not exist. What we once thought of as a void is actually a seething sea of virtual particles popping in and out of existence in the blink of an eye. These virtual particles are a direct consequence of Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This inherent uncertainty allows particles to briefly appear and disappear, borrowing energy from the vacuum itself. Even in the coldest, emptiest regions of space, quantum fluctuations create a constant buzz of activity. Pairs of particles and antiparticles spontaneously emerge from the vacuum, only to annihilate each other almost instantly. This quantum foam, as it is sometimes called, is the very antithesis of nothingness. Perhaps most astonishingly, these quantum fluctuations are not just a theoretical concept. They have observable effects on the physical world, such as the Casimir effect, where two uncharged metal plates in a vacuum are pushed together by the pressure of virtual particles. Quantum mechanics thus reveals that nothingness is not empty at all, but a dynamic, energetic state full of potential. The Big Bang Theory is our current best explanation for how the universe began. It proposes that approximately 13.8 billion years ago, all matter and energy in the cosmos was compressed into an incredibly dense, hot state. This primordial point then rapidly expanded and cooled, giving rise to the vast universe we observe today. In the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. This expansion caused the universe to grow from a size smaller than an atom to cosmic scales in an instant. As the universe continued to expand and cool, it allowed for the formation of fundamental particles, then atoms, and eventually the first stars and galaxies. The Big Bang Theory is supported by several key pieces of evidence. One is the cosmic microwave background radiation, a faint glow of light that fills the entire sky and represents the afterglow of the Big Bang. Another is the observed expansion of the universe, with distant galaxies moving away from us at increasing speeds. The theory also accurately predicts the abundance of light elements like hydrogen and helium in the cosmos. It is important to note that the Big Bang Theory does not explain what caused the initial expansion or what came before it. It only describes the evolution of the universe from that moment onward. Scientists continue to research and debate these deeper questions about the ultimate origin of our cosmos. The Big Bang Theory was first proposed by Georges Lemaitre, a Belgian physicist and Roman Catholic priest in the late 1920s. Lemaitre suggested that the universe began from a single primordial atom, which he called the cosmic egg. This idea laid the foundation for what would later become known as the Big Bang Theory. Lemaitre's groundbreaking concept was based on his observations of the redshift of distant galaxies, which indicated that the universe was expanding. He reasoned that if the universe was expanding, it must have been smaller in the past. Following this logic to its ultimate conclusion, Lemaitre proposed that the entire universe had originated from an incredibly dense and hot initial state. While Lemaitre's ideas were revolutionary, they did not immediately gain widespread acceptance. It was not until the 1940s and 50s that the theory began to gain traction, largely due to the work of other scientists like George Gamow and Ralph Alpher. They developed the theory further, predicting the existence of cosmic microwave background radiation, which was later discovered in 1965. The term Big Bang itself was coined somewhat ironically by astronomer Fred Hoyle, who was actually a proponent of the competing steady-state theory. Despite its initially dismissive intent, the name stuck and is now universally recognized as the prevailing theory of the origin of our universe. The Big Bang Theory, our current best explanation for the origin of the universe, is supported by several key pieces of evidence. First and foremost is the expansion of the universe. Observations of distant galaxies show they are moving away from us, and the farther away they are, the faster they're receding. This suggests that the universe is expanding in all directions, consistent with an explosive beginning. Another crucial piece of evidence is the cosmic microwave background radiation. This faint glow, discovered in 1965, permeates all of space and is considered the afterglow of the Big Bang. Its uniformity and temperature align perfectly with predictions made by the theory. The abundance of light elements in the universe also supports the Big Bang model. The theory accurately predicts the observed ratios of hydrogen, helium, and lithium in the cosmos, which were formed in the first few minutes after the Big Bang. Lastly, the distribution of galaxies in the universe matches what we'd expect from an expanding universe that began as a hot, dense state. Large-scale structures like galaxy clusters and cosmic voids align with computer simulations based on Big Bang cosmology, providing further evidence for this groundbreaking theory. The Big Bang theory provides a compelling explanation for the birth of our universe. According to this model, the cosmos began as an incredibly hot, dense point approximately 13.8 billion years ago. In a fraction of a second, this singularity rapidly expanded, initiating the creation of all matter and energy we observe today. As the universe cooled and expanded, it allowed for the formation of fundamental particles like quarks and electrons. These particles eventually combined to form the first atoms, primarily hydrogen and helium. Over time, gravity caused these atoms to clump together, forming the first stars and galaxies. The Big Bang theory is supported by several key pieces of evidence. One is the cosmic microwave background radiation, a faint glow permeating all of space. This radiation is essentially the afterglow of the Big Bang, providing a snapshot of the early universe. Another crucial piece of evidence is the observed expansion of the universe, with distant galaxies moving away from us at increasing speeds. While the Big Bang theory explains many aspects of our universe, it does not address what came before or what caused the initial expansion. Scientists continue to explore these questions, pushing the boundaries of our understanding of the cosmos and its origins. The Big Bang theory proposes that our universe began in an incredibly hot, dense state approximately 13.8 billion years ago. This initial state was not an explosion in space, but rather an expansion of space itself. All the matter and energy in the cosmos was compressed into an infinitesimally small point, known as a singularity. In this primordial state, the universe was so compact that the fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, unknown force. The temperature at this moment was unimaginably high, far beyond anything we can recreate in laboratories today. As the universe began to expand and cool, it underwent a series of transitions. Within the first fraction of a second, the fundamental forces separated, and the universe entered a period of rapid expansion called cosmic inflation. During this time, the universe grew exponentially, smoothing out any initial irregularities and setting the stage for the formation of matter as we know it. After inflation, the universe continued to expand and cool, allowing for the formation of subatomic particles, then simple atoms, and eventually the first stars and galaxies. This process of cosmic evolution has continued for billions of years, leading to the vast and complex universe we observe today. The universe, according to our current understanding based on the Big Bang model, is approximately 13.8 billion years old. This age estimate comes from a variety of observational evidence and theoretical calculations. Scientists have arrived at this figure by studying the cosmic microwave background radiation, the oldest light in the universe, and by measuring the expansion rate of the cosmos. Observations of the most distant galaxies and the chemical composition of ancient stars also contribute to our understanding of the universe's age. These measurements, combined with our knowledge of fundamental physics, allow cosmologists to trace the universe's history back to its earliest moments. It is important to note that this age represents the time since the Big Bang, which marks the beginning of the universe as we know it. Before this point, our current models of physics break down, and the nature of existence becomes unclear. The Big Bang itself is not considered the absolute beginning, but rather the earliest point we can reliably describe with our current scientific understanding. This age estimate has profound implications for our place in cosmic history. It suggests that the universe has undergone a long and complex evolution, from the formation of the first atoms to the emergence of galaxies, stars, and planets, ultimately leading to the conditions that allow for life as we know it. Cosmic microwave background radiation is the oldest light in the universe, a faint glow that fills all of space. This ancient radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. The discovery of this radiation in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory. It represents the afterglow of the Big Bang, the moment when our universe began. The existence of this uniform background radiation was predicted by the Big Bang theory before it was actually observed, making its detection a triumph for the theory. The cosmic microwave background radiation is remarkably uniform in all directions, which aligns with the idea that the early universe was hot, dense, and evenly distributed. This uniformity supports the concept that the universe expanded from a single point. Moreover, the temperature of this radiation, which is about 2.7 Kelvin, matches the predictions made by the Big Bang theory. Detailed measurements of the cosmic microwave background have revealed tiny fluctuations in temperature. These fluctuations are believed to be the seeds from which all cosmic structures, including galaxies and galaxy clusters, eventually formed. This connection between the early universe and the structures we see today further strengthens the Big Bang theory as our best explanation for the origin and evolution of the cosmos. Quantum fluctuations are tiny, rapid changes in energy that occur constantly at the smallest scales of the universe. These fluctuations are a fundamental aspect of quantum mechanics, the branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. In the quantum world, the principle of uncertainty reigns supreme. This principle states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. As a result, the quantum realm is characterized by a constant state of flux, where particles and energy seem to appear and disappear in the blink of an eye. These quantum fluctuations have profound implications for our understanding of the universe. They are believed to be the seeds from which all structure in the cosmos grew, from the smallest particles to the largest galaxies. During the earliest moments of the Big Bang, quantum fluctuations were amplified to cosmic scales, creating the tiny irregularities in the distribution of matter that eventually led to the formation of stars, planets, and everything we see around us today. Moreover, quantum fluctuations challenge our notion of empty space. Even in a perfect vacuum, devoid of all matter, these fluctuations persist. This suggests that what we perceive as empty space is actually a seething cauldron of virtual particles popping in and out of existence, lending credence to the idea that the vacuum itself contains energy. Quantum fluctuations play a crucial role in our understanding of the universe's origins. These tiny, unpredictable changes in energy levels occur at the smallest scales of reality, where the rules of quantum mechanics govern. In the earliest moments of the universe, quantum fluctuations were amplified to cosmic proportions, seeding the formation of galaxies and large-scale structures we observe today. During the inflationary period, which occurred a fraction of a second after the Big Bang, the universe expanded at an incredible rate. This rapid expansion stretched quantum fluctuations, transforming these microscopic variations into macroscopic differences in the distribution of matter and energy across space. These variations created areas of slightly higher and lower density in the early universe. Over time, gravity acted on these density differences, causing matter to clump together in denser regions and form the first stars and galaxies. The less dense areas became the vast, empty spaces between cosmic structures. In this way, the quantum world left its imprint on the large-scale structure of the universe. The concept of quantum fluctuations also relates to the very beginning of the universe itself. Some theories propose that our entire universe may have emerged from a quantum fluctuation in a pre-existing state, highlighting the profound connection between the quantum realm and the cosmos we inhabit. The quantum vacuum is a fundamental concept in quantum physics that challenges our intuitive understanding of emptiness. Unlike absolute nothingness, which implies a complete absence of everything, the quantum vacuum is a state of minimum energy that is far from empty. In the quantum vacuum, particles and antiparticles constantly pop into and out of existence in pairs. These virtual particles appear and disappear so quickly that they cannot be directly observed. However, their effects can be measured and have been experimentally verified. This constant flux of particles creates a sea of energy that permeates all of space. The existence of the quantum vacuum has profound implications for our understanding of the universe. It suggests that even in the absence of matter, space is not truly empty, but filled with potential energy and activity. This concept has led to fascinating theories about the nature of the cosmos, including ideas about the origin of the universe and the existence of dark energy. The quantum vacuum differs from absolute nothingness in its inherent energy and activity. While nothingness implies a complete void, the quantum vacuum is a dynamic state that plays a crucial role in the fabric of reality. It serves as a reminder that the universe is far more complex and mysterious than it might appear at first glance. Virtual particles are a fascinating aspect of quantum physics, emerging from the very fabric of space-time itself. These elusive entities pop into existence for the briefest of moments, appearing and disappearing in pairs faster than we can detect them directly. Their fleeting nature is intrinsically linked to the concept of quantum fluctuations, which describe the constant, subtle changes occurring at the smallest scales of reality. Quantum fluctuations arise from the inherent uncertainty principle of quantum mechanics. This principle states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. As a result, even in the apparent emptiness of space, energy levels are never truly at zero. Instead, they constantly fluctuate, giving rise to virtual particle pairs. These virtual particles play a crucial role in many quantum phenomena. They can briefly separate, with one particle having positive energy and its partner having negative energy, before rapidly reuniting and annihilating each other. This process happens countless times every second throughout the universe, creating a sort of quantum foam that underlies all of reality. The effects of virtual particles and quantum fluctuations extend far beyond the microscopic realm. They influence the properties of atoms, affect the strength of fundamental forces, and even contribute to the expansion of the universe itself. Understanding these quantum processes is essential for unraveling the deepest mysteries of our cosmos and pushing the boundaries of our scientific knowledge. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that describes the inherent limits of precision when measuring certain pairs of physical properties of particles. It states that we cannot simultaneously know both the exact position and momentum of a particle with perfect accuracy. The more precisely we measure one property, the less certain we become about the other. This principle has profound implications for our understanding of the universe at the smallest scales. It reveals that the subatomic world is not deterministic, but inherently probabilistic. Particles do not have fixed, definite properties until they are observed or measured. Quantum fluctuations are a direct consequence of the uncertainty principle. They refer to the constant, rapid changes in energy levels that occur in seemingly empty space. Even in a perfect vacuum, particles continually pop in and out of existence, borrowing energy from the vacuum for brief moments before disappearing again. These fluctuations are so fleeting that they do not violate the conservation of energy. The connection between the uncertainty principle and quantum fluctuations highlights the dynamic nature of the quantum world. It suggests that the fabric of space itself is not empty, but teeming with activity at the smallest scales, constantly creating and annihilating particle pairs. This phenomenon has far-reaching consequences, influencing everything from the properties of atoms to the evolution of the early universe. Quantum fluctuations are a fascinating aspect of the subatomic world, challenging our everyday notions of cause and effect. In the realm of quantum mechanics, the vacuum of space is not truly empty but filled with energy. This energy manifests as pairs of virtual particles that constantly pop into and out of existence. These fleeting particles, existing for mere fractions of a second, are a direct result of the uncertainty principle. This fundamental concept in quantum mechanics states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. As a consequence, the energy state of a system can fluctuate, allowing for the temporary creation of particle pairs. While these quantum fluctuations do not create lasting matter from absolute nothingness, they demonstrate that the quantum vacuum is far from empty. In fact, some theories suggest that these fluctuations played a crucial role in the early universe, potentially serving as the seeds for cosmic structures we observe today. The concept of quantum fluctuations, creating something from nothing, becomes particularly intriguing when considering theories about the origin of our universe. Some physicists propose that a large-scale quantum fluctuation could have triggered the Big Bang, essentially bringing our entire cosmos into existence. However, this remains a topic of ongoing research and debate in the scientific community. Scientists employ a range of sophisticated techniques to study and measure quantum fluctuations, those tiny, unpredictable changes in energy that occur at the subatomic level. One key method involves using ultra-sensitive detectors to observe the behavior of particles in carefully controlled environments. These detectors can pick up minute variations in energy levels, revealing the presence of quantum fluctuations. Another approach utilizes specialized lasers to probe quantum systems. By shining precisely calibrated light on particles, researchers can measure how the particles respond, providing insights into their quantum properties. This technique, known as laser spectroscopy, allows scientists to detect fluctuations that would otherwise be too small to observe. Researchers also rely on advanced mathematical models and computer simulations to predict and analyze quantum fluctuations. These theoretical tools help scientists interpret experimental data and develop new hypotheses about quantum behavior. By comparing real-world observations with computer-generated predictions, researchers can refine their understanding of these elusive phenomena. Perhaps most intriguingly, scientists have developed quantum sensors that exploit the very nature of quantum fluctuations to make incredibly precise measurements. These sensors can detect tiny changes in gravity, magnetic fields, and other forces, opening up new possibilities for studying everything from the Earth's crust to distant galaxies. As technology continues to advance, our ability to observe and measure quantum fluctuations grows, pushing the boundaries of our understanding of the universe at its most fundamental level. Cosmic inflation theory proposes that the early universe underwent a period of rapid, exponential expansion in the first fraction of a second after the Big Bang. This expansion happened faster than the speed of light, stretching the fabric of space-time and expanding the universe to a vast size almost instantaneously. The theory was developed to explain several puzzling features of our universe, including its remarkable uniformity and flatness. It suggests that before inflation, the universe was incredibly tiny, perhaps smaller than a subatomic particle. During inflation, this minuscule region expanded to cosmic scales, smoothing out any initial irregularities and creating the large-scale structure we observe today. Inflation also provides a mechanism for the formation of galaxies and other cosmic structures. As the universe expanded, tiny quantum fluctuations were amplified into slight density variations. These variations became the seeds for the cosmic web of galaxies and galaxy clusters we see in the present-day universe. While cosmic inflation theory elegantly solves many cosmological problems, it remains an active area of research. Scientists continue to search for observational evidence to support or refine the theory, particularly through studies of the cosmic microwave background radiation and gravitational waves. Alan Guth, an American theoretical physicist and cosmologist, proposed the inflation theory in 1980. He developed this groundbreaking idea to address several puzzling issues with the standard Big Bang model that scientists had been grappling with for years. The inflation theory suggests that the early universe underwent a period of rapid, exponential expansion in the tiniest fraction of a second after the Big Bang. This brief but intense growth spurt would have caused the universe to expand faster than the speed of light, stretching space itself to an enormous size almost instantaneously. Guth's theory elegantly solved several cosmological problems. It explained why the universe appears so uniform on large scales, a phenomenon known as the horizon problem. It also accounted for the flatness of space and the absence of magnetic monopoles, which were predicted by some theories but never observed. The inflation theory has since become a cornerstone of modern cosmology, providing a framework for understanding the early universe and the origins of cosmic structure. While it continues to be refined and debated, its ability to explain observed phenomena has made it a crucial part of our understanding of the cosmos. Inflation theory enhances our understanding of the early universe by addressing key limitations in the standard Big Bang model. This theory proposes that the universe underwent an incredibly rapid expansion in its first fraction of a second, growing from subatomic scales to cosmic proportions almost instantaneously. This brief period of exponential growth helps explain several puzzling aspects of our cosmos. For instance, it accounts for the remarkable uniformity we observe in the cosmic microwave background radiation across vast distances. Inflation suggests that regions of space now far apart were once in close contact before being stretched apart, explaining their similar properties. Inflation also provides a mechanism for the formation of large-scale structures in the universe. Quantum fluctuations, infinitesimally small variations in the fabric of spacetime, were amplified to cosmic scales during this rapid expansion. These fluctuations became the seeds for galaxies and galaxy clusters we see today. Moreover, inflation theory offers a solution to the flatness problem, explaining why the universe appears to have a geometry so close to perfectly flat. The immense stretching of space during inflation would have smoothed out any initial curvature, resulting in the nearly flat universe we observe. By addressing these and other cosmological questions, inflation theory has become a crucial complement to the Big Bang model, providing a more complete picture of our universe's earliest moments and subsequent evolution. Inflation theory addresses several key issues in cosmology that were left unexplained by the traditional Big Bang model. One of the most significant problems it solves is the horizon problem. This refers to the puzzling uniformity of the cosmic microwave background radiation across vast distances in the universe that should not have been in causal contact. Inflation proposes that the early universe underwent a period of exponential expansion, allowing regions that were once connected to expand far beyond the observable horizon, explaining this uniformity. Another issue inflation resolves is the flatness problem. Observations show that the universe is remarkably close to being spatially flat, which requires an extremely precise initial density. Inflation naturally produces this flatness by stretching the universe so dramatically that any initial curvature would be smoothed out, much like inflating a balloon makes its surface appear flatter. Inflation also provides a solution to the magnetic monopole problem. Many grand unified theories predict the existence of magnetic monopoles, which should have been produced in abundance in the early universe. However, we have never observed them. Inflation explains their absence by diluting their density to such an extent that we would not expect to find any in our observable universe. Lastly, inflation offers a mechanism for the origin of cosmic structure. It proposes that quantum fluctuations in the inflationary field were stretched to cosmic scales, providing the seeds for the formation of galaxies and large-scale structures we observe today. This elegant solution connects the quantum world with the largest scales of the universe, offering a comprehensive framework for understanding cosmic evolution. The inflation theory, a cornerstone of modern cosmology, is supported by several key pieces of evidence. One of the most compelling is the remarkable uniformity of the cosmic microwave background radiation. This faint afterglow of the early universe is incredibly smooth, with temperature variations of only about 1 part in 100,000. Such uniformity would be difficult to explain without a period of rapid expansion that smoothed out any initial irregularities. Another crucial piece of evidence is the flatness of space. Observations indicate that the universe is nearly perfectly flat, which aligns with the predictions of inflationary models. This flatness would be highly improbable without an inflationary period, as even tiny deviations from flatness in the early universe would have been amplified over time. The theory also explains the origin of cosmic structure. Inflation proposes that quantum fluctuations stretched to cosmic scales during the rapid expansion seeded the formation of galaxies and large-scale structures we observe today. This connection between the smallest quantum scales and the largest cosmic structures is a powerful aspect of the theory. Lastly, the absence of magnetic monopoles, which many theories predict should have been produced in abundance in the early universe, is consistent with inflation. The rapid expansion would have diluted these particles to undetectable levels, explaining why we have never observed them. These lines of evidence, while not conclusive, provide strong support for the inflation theory and its place in our understanding of the early universe. Inflation provides a compelling explanation for the remarkable uniformity observed in the cosmic microwave background. This ancient light, which has traveled across the universe for billions of years, appears strikingly consistent in all directions we look. Such uniformity posed a significant challenge to our understanding of the early universe, as regions on opposite sides of the sky should not have been in causal contact given the age and expansion rate of the universe. The theory of cosmic inflation resolves this puzzle by proposing that the very early universe underwent a brief period of exponential expansion. During this fleeting moment, lasting only a fraction of a second, the universe grew by a factor of at least 10 raised to the power of 26. This rapid expansion took a minuscule, causally connected region of space and stretched it to cosmic scales. Before inflation, this tiny patch of the primordial universe had time to reach thermal equilibrium, resulting in a uniform temperature and density. As inflation dramatically expanded this region, it preserved this uniformity across vast distances. The cosmic microwave background we observe today is the afterglow of this initially small, uniform region that was stretched to encompass our entire observable universe. Inflation thus explains how regions of the sky that appear to be causally disconnected can share the same properties. It provides a natural mechanism for the observed uniformity, solving the horizon problem and offering a framework that aligns with our observations of the cosmic microwave background. Eternal inflation presents a mind-bending concept that challenges our understanding of the universe and its origins. This theory suggests that our cosmos is just one of countless bubbles in an ever-expanding sea of space-time, continuously giving birth to new universes. The implications of eternal inflation are profound. It proposes that the process of cosmic expansion, which began with the Big Bang, never truly ends. Instead, it continues indefinitely, creating new regions of space-time that expand exponentially. Within this vast, ever-growing multiverse, regions can stop inflating and form discrete universes like our own. This concept drastically alters our view of cosmic history and structure. If true, it means our universe is not unique, but part of a much larger, possibly infinite, multiverse. Each universe within this multiverse could have different physical laws, constants, and properties, leading to an astounding variety of possible realities. Eternal inflation also has implications for the fate of our own universe. While our local region might eventually experience heat death or a big crunch, the process of inflation would continue elsewhere, ensuring the perpetual creation of new universes. This endless cycle of creation challenges our notions of cosmic beginnings and endings, suggesting a reality far more complex and expansive than we ever imagined. The first fraction of a second after the Big Bang was a period of incredible change and rapid expansion. In this infinitesimally small window of time, the universe as we know it began to take shape. Immediately following the Big Bang, the universe was an unimaginably hot and dense state of pure energy. As it expanded and cooled, fundamental forces began to separate. Gravity split off first, followed by the strong nuclear force, and then the weak nuclear force and electromagnetism. During this brief moment, the universe underwent a period of exponential expansion called cosmic inflation. This expansion happened faster than the speed of light, causing the universe to grow from smaller than an atom to about the size of a grapefruit in just a tiny fraction of a second. As the universe continued to cool, it became possible for the first particles to form. Quarks, electrons, and other fundamental particles emerged from the primordial energy soup. These particles would later combine to form the first atomic nuclei, setting the stage for the formation of matter as we know it today. The early universe was unimaginably hot. Moments after the Big Bang, temperatures soared to over 100 billion degrees Celsius. This extreme heat was a result of the incredible density and energy of the newly formed cosmos. As the universe rapidly expanded, it began to cool. Within the first second, temperatures dropped to about 10 billion degrees Celsius. By the time the universe was a few minutes old, it had cooled further to about 1 billion degrees Celsius. This cooling trend continued as the universe grew. After about 380,000 years, the temperature had fallen to around 3,000 degrees Celsius. At this point, the universe became transparent to light, releasing the cosmic microwave background radiation we can still detect today. The temperature of the universe has continued to decrease over billions of years. Today, the average temperature of empty space is a frigid 2.7 degrees above absolute zero Celsius, a stark contrast to its fiery beginnings. In the earliest moments of our universe, the fundamental forces we know today were unified into a single, incredibly powerful force. As the universe expanded and cooled after the Big Bang, these forces began to separate in a process called symmetry breaking. The first force to break away was gravity, becoming distinct when the universe was just a fraction of a second old. This separation allowed for the formation of space and time as we understand them. Next, the strong nuclear force split off, enabling the formation of quarks and other subatomic particles. As the universe continued to cool, the electromagnetic force and the weak nuclear force separated. This final split occurred when the universe was about 1/100th of a second old. The separation of these forces allowed for the diverse interactions between particles that we observe in the universe today. This process of force separation was crucial for the formation of matter and the structures we see in the cosmos. It set the stage for the complex physics that governs our universe, from the smallest atoms to the largest galaxies. The electroweak epoch marks a crucial phase in the early universe, occurring mere fractions of a second after the Big Bang. During this time, the universe had cooled enough for the fundamental forces of nature to begin separating, yet remained incredibly hot by our standards today. In this epoch, two of the four fundamental forces we know today, the electromagnetic force and the weak nuclear force, were unified into a single electroweak force. This unification meant that particles which we now consider distinct, such as photons and W and Z bosons, were essentially interchangeable. As the universe continued to expand and cool, it reached a critical temperature. At this point, the symmetry between the electromagnetic and weak forces broke, causing them to separate into the distinct forces we observe today. This process, known as electro-weak symmetry breaking, was accompanied by the emergence of the Higgs field, which gives particles their mass. The electro-weak epoch represents a window into the fundamental nature of our universe, showcasing how the forces that shape our world today were once merged in the extreme conditions of the early cosmos. It highlights the dynamic and evolving nature of the universe, where even the basic rules of physics have changed over time. In the earliest moments of our universe, a sea of pure energy existed in an unimaginably hot and dense state. As this primordial fireball began to expand and cool, the first particles emerged from this energy soup. This process, known as particle formation, occurred just fractions of a second after the Big Bang. The initial particles to materialize were quarks and leptons, the fundamental building blocks of matter. Quarks quickly combined to form protons and neutrons, while electrons, a type of lepton, remained separate. This era, often called the quark epoch, lasted for only microseconds, but set the stage for the formation of atoms. As the universe continued to expand and cool, protons and neutrons began to combine, forming the nuclei of the lightest elements, hydrogen and helium. This process, known as nucleosynthesis, occurred within the first few minutes of the universe's existence. The formation of these first particles and light elements laid the groundwork for the complex structures we see in the universe today. From these humble beginnings, stars, galaxies, and eventually planets would form, showcasing the remarkable journey from energy to the diverse cosmos we observe. Antimatter played a crucial role in the early universe, shaping the very fabric of existence as we know it today. In the first fractions of a second after the Big Bang, the universe was an incredibly hot, dense soup of particles and their antimatter counterparts. These pairs of matter and antimatter particles were constantly being created and annihilated in a cosmic dance of energy conversion. As the universe expanded and cooled, a process called baryogenesis occurred. This led to a slight imbalance between matter and antimatter, with matter gaining a tiny advantage. For every billion antimatter particles, there were 1,000,000,001 matter particles. When matter and antimatter collided and annihilated, they released enormous amounts of energy in the form of light. This process continued until nearly all the antimatter was gone, leaving behind the excess matter that forms our universe today. The energy released during this period of annihilation contributed to the intense radiation that filled the early universe. This radiation, now cooled and stretched by the expansion of space, can still be detected today as the cosmic microwave background radiation. It serves as a fossil record of the early universe, providing valuable insights into cosmic history. The mystery of why there was more matter than antimatter in the early universe remains one of the biggest questions in cosmology. Understanding this asymmetry could help explain why our universe is composed of matter rather than antimatter and why we exist at all. The study of antimatter in the early universe continues to push the boundaries of our knowledge about the fundamental nature of reality. In the early stages of our universe, radiation reigned supreme. This era, known as the radiation-dominated epoch, was characterized by an abundance of energetic photons that far outweighed the influence of matter. As the universe expanded and cooled, a profound shift occurred. The transition from radiation dominance to matter dominance unfolded gradually over time. As the universe continued to expand, the energy density of radiation decreased more rapidly than that of matter. This difference in behavior stems from the fundamental properties of radiation and matter. While the energy of radiation diminishes as the universe expands, the energy of matter remains relatively constant. Around 380,000 years after the Big Bang, a pivotal moment arrived. At this point, the energy densities of radiation and matter became equal. This marked the beginning of the matter-dominated era, a crucial phase in cosmic evolution. From this moment forward, matter began to exert a stronger influence on the universe's structure and development. This transition had profound implications for the formation of cosmic structures. As matter became the dominant force, it began to clump together under the influence of gravity. This clustering of matter laid the foundation for the formation of galaxies, stars, and ultimately, the complex universe we observe today. In the earliest moments after the Big Bang, the universe was an incredibly hot and dense soup of fundamental particles. As it rapidly expanded and cooled, the first elements began to form through a process called Big Bang nucleosynthesis. This occurred when the universe was only a few minutes old. The first and most abundant element to emerge was hydrogen, the simplest atom with just one proton and one electron. Helium, the second lightest element, was also produced in significant quantities during this early period. These two elements, along with trace amounts of lithium, were the only ones created in the immediate aftermath of the Big Bang. The formation of these primordial elements was crucial for the future development of the universe. Hydrogen and helium would later serve as the building blocks for the first stars, which would go on to create heavier elements through nuclear fusion in their cores. It is remarkable to consider that the majority of hydrogen atoms in the universe today, including those in the water we drink, were forged in the intense conditions of the early universe billions of years ago. This connection to the cosmic past highlights the profound influence of the Big Bang on the composition of our universe. Big Bang nucleosynthesis is a crucial process that occurred in the early moments of our universe. It began approximately 3 minutes after the Big Bang and lasted for about 17 minutes. During this brief but significant period, the universe was a hot, dense soup of subatomic particles, primarily protons and neutrons. As the universe expanded and cooled, these particles began to combine, forming the first atomic nuclei. The majority of nuclei produced were those of hydrogen, the simplest and most abundant element in the universe. Helium nuclei were also formed in substantial quantities, accounting for about 25% of the universe's mass. Trace amounts of lithium were created as well. This process is responsible for determining the initial composition of the universe. The abundance of elements we observe today aligns remarkably well with predictions based on our understanding of Big Bang nucleosynthesis, providing strong support for the Big Bang theory. Interestingly, all heavier elements were formed much later in the history of the universe, primarily through stellar nucleosynthesis in stars and during supernova explosions. Big Bang nucleosynthesis set the stage for the cosmic evolution that followed, influencing the formation of the first stars and galaxies. In the first few minutes after the Big Bang, the universe was an incredibly hot and dense soup of particles. As it expanded and cooled, conditions became just right for the formation of the lightest elements. This process, known as Big Bang nucleosynthesis, occurred when the universe was merely seconds to minutes old. During this brief window, protons and neutrons could fuse together to form the nuclei of hydrogen and helium, along with trace amounts of lithium. These elements are considered light because they have few protons and neutrons. The universe at this time was still too hot and energetic for heavier elements to form and remain stable. The formation of these light elements was limited by the rapidly changing conditions in the expanding universe. As it continued to cool and expand, the density decreased, making it increasingly difficult for particles to collide and fuse. This effectively halted the production of elements heavier than lithium. It would take hundreds of millions of years before the first stars formed, providing the extreme temperatures and pressures necessary to forge heavier elements through stellar nucleosynthesis. This explains why the early universe was dominated by hydrogen and helium, with only small amounts of other light elements present. The formation of the first atoms marks a crucial milestone in the early universe, occurring approximately 380,000 years after the Big Bang. This period, known as the era of recombination, saw the universe cooled sufficiently for electrons to combine with protons, forming the simplest atom, hydrogen. Before this time, the universe was an intensely hot, dense plasma of particles, too energetic to allow stable atomic structures. As expansion continued and temperatures dropped, the conditions finally became suitable for atoms to exist without immediately being torn apart by the surrounding energy. This atomic formation had a profound effect on the nature of the cosmos. The newly formed atoms allowed light to travel freely through space for the first time, releasing what we now observe as the cosmic microwave background radiation. This ancient light continues to permeate the universe, providing valuable insights into its earliest stages. The creation of the first atoms set the stage for the formation of more complex structures, eventually leading to the diverse cosmic landscape we observe today. From these humble beginnings, the universe would go on to form stars, galaxies, and ultimately the conditions necessary for life as we know it. The cosmic abundance of elements provides strong evidence supporting the Big Bang theory. Hydrogen and helium, the two lightest elements, dominate the universe, making up about 99% of all visible matter. This overwhelming prevalence aligns perfectly with predictions from Big Bang nucleosynthesis, the process by which these elements formed in the early universe. During the first few minutes after the Big Bang, conditions were ideal for the creation of hydrogen and helium nuclei. As the universe expanded and cooled, it quickly became too cold for further nuclear fusion, leaving these light elements as the primary components of the cosmos. Heavier elements, which make up only about 1% of cosmic matter, were largely produced later in the cores of stars or during stellar explosions. Observations of distant galaxies and intergalactic gas clouds consistently show this same elemental composition, regardless of their location or age in the universe. This uniformity suggests a common origin for all matter, precisely what the Big Bang theory proposes. Moreover, the specific ratios of hydrogen to helium and their isotopes match theoretical calculations based on the Big Bang model with remarkable accuracy. The cosmic abundance of elements thus serves as a fossil record of the early universe, preserving the conditions present during the first moments of cosmic history. This elemental fingerprint, consistent across the observable universe, stands as one of the strongest pillars supporting the Big Bang theory, alongside cosmic microwave background radiation and the expansion of the universe. The formation of heavier elements in the universe is a fascinating story of cosmic evolution. In the early moments after the Big Bang, the universe consisted primarily of hydrogen and helium, the two lightest elements. These elements formed during the first few minutes of the universe's existence in a process called Big Bang nucleosynthesis. As the universe cooled and expanded, gravity caused these primordial gases to coalesce into the first stars. These early stars, much more massive than our Sun, became cosmic furnaces where nuclear fusion began to forge heavier elements. In their cores, hydrogen fused into helium and helium fused into carbon and oxygen. This process, known as stellar nucleosynthesis, continued to create elements up to iron. However, the creation of elements heavier than iron required a different mechanism. When massive stars exhausted their fuel, they exploded as supernovae, releasing enormous amounts of energy. These violent explosions created the conditions necessary for rapid neutron capture, or the R process, which produced elements heavier than iron, such as gold, silver, and uranium. Another source of heavy elements came from the collisions of neutron stars. These incredibly dense stellar remnants, when they merged, created spectacular explosions that rivaled supernovae in their intensity. These cosmic events, only recently observed, have been confirmed as significant sources of heavy elements in the universe, enriching the cosmic environment and providing the building blocks for future generations of stars and planets. Stars are the cosmic factories that forge most of the elements in the universe. At their cores, stars fuse hydrogen into helium through nuclear reactions. releasing enormous amounts of energy in the process. This energy production is what makes stars shine and supports them against the crushing force of their own gravity. As stars age, they begin to fuse helium into heavier elements like carbon and oxygen. In the most massive stars, this process continues, creating progressively heavier elements up to iron. These elements are then dispersed into space when the star dies, either through stellar winds or explosive events like supernovae. Supernovae play a crucial role in element formation. These powerful explosions create conditions of extreme temperature and pressure, allowing for the creation of elements heavier than iron, such as gold, silver, and uranium. These newly formed elements are then scattered across space, where they can eventually become part of new stars, planets, and even living organisms. The elements in our bodies, the iron in our blood, the calcium in our bones, were all forged in the hearts of stars long ago. This cosmic recycling process continues today, with new stars forming from the remnants of previous stellar generations, ensuring a constant cycle of element creation and dispersal throughout the universe. The formation of the first large-scale structures in the universe began in the aftermath of the Big Bang. As the cosmos expanded and cooled, tiny quantum fluctuations in the early universe were amplified by inflation, creating areas of slightly higher and lower density. These minute differences in density became the seeds for cosmic structure. Gravity played a crucial role in this process. In regions with slightly higher density, matter began to clump together, attracting more and more material over time. Meanwhile, less dense areas became increasingly empty as matter was drawn away. This process, known as gravitational collapse, led to the formation of vast cosmic filaments and voids. Over millions of years, these growing concentrations of matter formed the first galaxies. These early galaxies were much smaller and more irregular than those we see today. They began to cluster together due to their mutual gravitational attraction, forming the first galaxy groups and protoclusters. As time progressed, these structures continued to grow and merge, eventually giving rise to the cosmic web we observe today. This web consists of massive galaxy clusters connected by long filaments of galaxies, with vast voids in between. This process of structure formation is ongoing, with gravity continuing to shape the large-scale structure of the universe over billions of years. The cosmic web is the vast, intricate structure that forms the backbone of our universe. It consists of an enormous network of galaxies, galaxy clusters, and filaments of dark matter stretching across the cosmos. This web-like pattern emerged in the early stages of the universe's formation, shaped by the interplay of gravity and the expansion of space. As the universe cooled after the Big Bang, tiny fluctuations in the distribution of matter began to grow. Regions with slightly more matter exerted a stronger gravitational pull, drawing in surrounding material. Over time, this process of attraction and accumulation led to the formation of long, thread-like filaments of dark matter and gas. These filaments serve as cosmic highways, guiding the flow of matter across vast distances. Where filaments intersect, we find dense clusters of galaxies. In contrast, the spaces between filaments, known as cosmic voids, are relatively empty regions spanning millions of light years. The cosmic web continues to evolve to this day, with galaxies and clusters moving along the filaments, gradually coming together to form even larger structures. This ongoing process of cosmic evolution provides astronomers with valuable insights into the fundamental forces shaping our universe and the distribution of visible and dark matter throughout space. Galaxies begin their lives as vast clouds of hydrogen and helium gas, remnants from the early universe. These primordial clouds slowly collapse under their own gravity, forming dense pockets where stars are born. As more stars ignite, their combined gravitational pull attracts additional gas and dust, gradually shaping the nascent galaxy. Over billions of years, galaxies grow through a combination of internal star formation and mergers with other galaxies. Smaller galaxies often collide and combine to form larger ones, a process that continues to this day. Our own Milky Way, for instance, is currently absorbing several smaller satellite galaxies and is on a collision course with the neighboring Andromeda galaxy. As galaxies evolve, they develop distinct structures. Some become spirals with graceful arms stretching outward from a central bulge, while others take on an elliptical shape. The type of galaxy that forms depends on factors such as its initial mass, rotation, and history of mergers. Interestingly, galaxy evolution is not a one-way street. Violent events like collisions can dramatically alter a galaxy shape, transforming spirals into ellipticals or creating irregular galaxies with no defined structure. The evolution of galaxies is also influenced by the mysterious dark matter that permeates the universe. This invisible substance provides additional gravitational force, helping to shape galactic structures and affecting how galaxies interact with one another. As we continue to study distant galaxies, we gain new insights into these cosmic behemoths and their role in the grand tapestry of the universe. Dark matter plays a crucial role in the formation of cosmic structures, acting as the gravitational scaffolding upon which the visible universe is built. This mysterious substance, which does not interact with light or other forms of electromagnetic radiation, comprises about 85% of all matter in the universe. Its gravitational influence is fundamental to the growth of galaxies, galaxy clusters, and the largest structures we observe in the cosmos. In the early universe, dark matter began to clump together under its own gravity, forming dense regions that attracted normal matter. These dark matter concentrations created gravitational wells, drawing in hydrogen and helium gas. As this gas cooled and condensed, it formed the first stars and galaxies within the dark matter halos. The presence of dark matter significantly accelerated the process of structure formation. Without it, the ordinary matter in the universe would have taken far longer to coalesce into the cosmic web we see today. Dark matter's gravitational effects also explain the observed rotational speeds of galaxies and the movement of galaxies within clusters, which cannot be accounted for by visible matter alone. As we continue to map the distribution of dark matter in the universe, we gain deeper insights into how cosmic structures evolved over billions of years. This invisible component remains one of the most intriguing mysteries in modern cosmology, driving ongoing research and shaping our understanding of the universe's architecture. Galaxy clusters and superclusters form through a process of cosmic assembly that spans billions of years. These immense structures begin their journey in the early universe, where tiny fluctuations in the density of matter, originating from quantum effects during the inflationary period, set the stage for cosmic growth. As the universe expands and cools, gravity takes hold of these slight irregularities, causing denser regions to attract more matter. Over time, this process accelerates, with larger structures exerting stronger gravitational pull. Individual galaxies form first, then begin to congregate into groups and small clusters under their mutual gravitational attraction. These galaxy clusters continue to merge and grow, often along vast filaments of dark matter that form the cosmic web. As clusters collide and combine, they form ever larger structures. The most massive of these become galaxy superclusters, enormous collections of thousands of galaxies spanning hundreds of millions of light-years. This hierarchical structure formation continues to shape our universe today. Observations reveal that galaxies and clusters are still moving along cosmic highways, gradually assembling into even larger structures. This ongoing process of cosmic construction provides astronomers with a living laboratory to study the forces that have shaped our universe over its long history. Cosmic voids are vast regions of space that contain very few galaxies, stars, or other cosmic structures. These enormous empty areas can span hundreds of millions of light-years across, dwarfing even the largest galaxy clusters. Cosmic voids are not truly empty. as they still contain small amounts of gas and dark matter, but their density is far lower than the cosmic average. These cosmic deserts play a crucial role in the formation of large-scale structures in the universe. As matter in the early universe began to clump together under the influence of gravity, it naturally left behind regions with less material. Over time, these underdense areas grew larger as more matter was pulled away from them, eventually forming the cosmic voids we observe today. The existence of cosmic voids is intimately linked to the web-like structure of the universe. As matter flows out of the voids, it accumulates along the edges, forming dense filaments and walls. These filaments intersect at nodes where galaxy clusters form, creating a cosmic web that resembles a sponge-like structure on the grandest scales. Studying cosmic voids helps astronomers understand the distribution of matter in the universe and test theories of cosmic evolution. The size, shape, and number of voids provide valuable information about the nature of dark energy and the overall expansion of the universe. As we continue to map these colossal empty regions, we gain deeper insights into the fundamental forces shaping our cosmic home. The distribution of matter in the universe has undergone a remarkable transformation since the Big Bang. In the earliest moments, matter was spread almost uniformly across the cosmos, with only tiny fluctuations in density. As the universe expanded and cooled, these minute variations began to grow under the influence of gravity. Over billions of years, areas with slightly more matter attracted additional material, slowly forming the cosmic web we observe today. This web consists of vast, nearly empty voids, surrounded by filaments of galaxies and dark matter. At the intersections of these filaments, we find massive galaxy clusters, the largest gravitationally bound structures in the universe. This evolution from near uniformity to a complex, clustered structure is driven by the interplay between the expansion of space and the attractive force of gravity. Dark energy, a mysterious force causing the universe to expand at an accelerating rate, also plays a crucial role in this cosmic ballet, counteracting the pull of gravity on the largest scales. Today, we see a universe where matter is highly clustered on small scales, forming stars, galaxies, and galaxy clusters, while appearing more uniform when viewed on the largest cosmic scales. This distribution continues to evolve, with galaxy clusters merging and voids growing larger as the universe expands. While the Big Bang theory remains the most widely accepted model for the origin of the universe, several alternative theories have been proposed by scientists over the years. One such theory is the steady-state model, which suggests that the universe has always existed and continues to expand, with new matter constantly being created to maintain a constant density. Although this theory has largely fallen out of favor, it sparked important debates in cosmology. Another alternative is the oscillating universe theory, which proposes that the universe undergoes cycles of expansion and contraction. In this model, the current expansion would eventually reverse, leading to a big crunch followed by another Big Bang. This idea addresses the question of what came before our current universe. Some scientists have also proposed the idea of a multiverse, suggesting that our universe is just one of many. This concept encompasses various models, including the idea of parallel universes, or bubble universes, that may have different physical laws and constants. While these ideas are highly speculative, they push the boundaries of our understanding of cosmology. More recently, some researchers have explored the possibility of an eternal inflation model, where our observable universe is just a small part of an ever-expanding cosmic landscape. These alternative theories continue to challenge our assumptions and drive further research into the nature and origin of the universe. The steady-state theory was a cosmological model proposed in the mid-20th century as an alternative to the Big Bang theory. It posited that the universe has always existed and will continue to exist in a constant, unchanging state. According to this theory, as the universe expands, new matter is continuously created to maintain a constant average density throughout space and time. Proponents of the steady-state theory, including Fred Hoyle, Hermann Bondi, and Thomas Gold, argued that the universe looks the same at all times and in all directions. They suggested that the observed expansion of the universe was balanced by the continuous creation of matter, maintaining a steady state of cosmic equilibrium. However, the steady-state theory faced significant challenges as new observational evidence emerged. The discovery of the cosmic microwave background radiation in 1965 provided strong support for the Big Bang theory and dealt a severe blow to the steady-state model. This faint afterglow from the early universe was consistent with the predictions of the Big Bang, but could not be easily explained by the steady-state theory. Further observations, such as the abundance of light elements in the universe and the evolution of galaxies over cosmic time, continued to favor the Big Bang model. As a result, the scientific community gradually abandoned the steady-state theory in favor of the Big Bang theory, which better explained the growing body of observational evidence about the origin and evolution of the universe. The cyclic model of the universe presents a fundamentally different view of cosmic history and future compared to the widely accepted Big Bang theory. While the Big Bang theory proposes that our universe began from a singularity and has been expanding ever since, the cyclic model suggests that the universe goes through endless cycles of expansion and contraction. In the cyclic model, our current universe is just one phase in an eternal series of universes. Each cycle begins with a bang and ends with a crunch, followed by another bang. This process repeats indefinitely, with each cycle lasting perhaps 1 trillion years. The model proposes that the end of one universe triggers the birth of the next, creating a never-ending cosmic dance. One key difference is that the cyclic model eliminates the need for a beginning of time. It suggests that the universe has always existed and will continue to exist forever, cycling through periods of expansion and contraction. This contrasts with the Big Bang theory, which points to a definite beginning of our universe about 13.8 billion years ago. The cyclic model also offers an alternative explanation for the observed cosmic acceleration. Instead of dark energy causing eternal expansion, as in the Big Bang model, the cyclic model proposes that this acceleration eventually reverses, leading to the next cosmic contraction. While both theories continue to be debated, the Big Bang model remains the prevailing explanation among most cosmologists today. The ekpyrotic universe theory offers an alternative explanation to the Big Bang for the origin and evolution of our cosmos. This model proposes that our universe began not with a sudden explosion, but with the collision of two vast, flat membranes, or branes, in a higher dimensional space. According to this theory, these branes exist in a realm with more dimensions than the 3 spatial dimensions we observe. They move through this higher dimensional space, occasionally colliding with tremendous force. Each collision triggers a new cycle of universal expansion, leading to the universe we see today. Proponents of the ekpyrotic model suggest it solves some problems associated with the Big Bang theory, such as the horizon problem and the flatness problem, without requiring cosmic inflation. They argue that the slow approach of the branes before collision naturally creates the conditions necessary for our observed universe. Critics of the theory point out that it lacks observational evidence and relies on speculative physics beyond our current ability to test. Despite these challenges, the ekpyrotic universe theory remains an active area of research in theoretical cosmology, offering a thought-provoking alternative to conventional models of cosmic origins. String theory proposes a revolutionary approach to understanding the fundamental nature of the universe. At its core, this theory suggests that the basic building blocks of reality are not point-like particles, but tiny, vibrating strings of energy. These strings, infinitesimally small and existing in multiple dimensions, vibrate in different ways to create all the particles and forces we observe in the cosmos. In the context of the universe's origin, string theory offers a unique perspective. It suggests that the Big Bang, rather than being the absolute beginning, might have been a collision or interaction between vast, multi-dimensional membranes, often called brains. This concept, known as the ekpyrotic scenario, proposes that our universe emerged from this cosmic collision, expanding and cooling to form the structures we see today. String theory also introduces the idea of a multiverse, where our universe might be just one of many, each with its own physical laws and constants. This framework potentially explains why our universe seems so finely tuned for life, as it could be one of countless universes with varying properties. However, it's important to note that while string theory is mathematically elegant and offers intriguing explanations for cosmic phenomena, it remains highly speculative. Scientists continue to work on developing ways to test its predictions and validate its complex mathematical framework in the observable universe. The multiverse hypothesis proposes that our universe is not alone, but part of a vast collection of universes, each with its own unique properties and physical laws. This concept challenges the traditional view of a single, all-encompassing universe and suggests that reality is far more expansive and diverse than we once thought. According to this theory, our universe's origin might be just one of countless cosmic births. The idea is that universes can spawn from quantum fluctuations or bubble off from other universes, creating a continually expanding cosmic landscape. Each universe within this multiverse could have different fundamental constants, varying laws of physics, and potentially even different dimensions. This hypothesis offers a potential explanation for the fine-tuning of our universe. The seemingly perfect conditions that allow for the existence of stars, planets, and life might not be a cosmic coincidence or the result of intelligent design, but rather a natural outcome in a vast multiverse where all possibilities are realized. While the multiverse hypothesis is intriguing, it remains a theoretical concept. Scientists continue to search for ways to test and potentially prove or disprove this idea, pushing the boundaries of our understanding of cosmic origins and the nature of reality itself. While the Big Bang theory remains the most widely accepted model for the origin and evolution of the universe, several alternative theories have gained attention in the scientific community. One notable alternative is the steady-state theory, which proposes that the universe has always existed and continues to expand while maintaining a constant average density. However, this theory has largely fallen out of favor due to observational evidence supporting the Big Bang. Another alternative is the cyclic model, which suggests that the universe undergoes endless cycles of expansion and contraction. This theory posits that our current universe is just one in a series of universes that have existed before and will exist after ours. The cyclic model attempts to address some of the challenges faced by the Big Bang theory, such as the nature of the initial singularity. The ekpyrotic scenario is a more recent proposal that envisions our universe as a three-dimensional membrane existing in a higher dimensional space. In this model, the Big Bang resulted from a collision between our membrane and a parallel universe membrane. This theory aims to explain the uniformity of the cosmic microwave background radiation without relying on cosmic inflation. It is important to note that while these alternative theories offer intriguing possibilities, they currently lack the robust observational evidence that supports the Big Bang model. Scientists continue to explore and refine these alternatives, but the Big Bang theory remains the most comprehensive and well-supported explanation for the origin and evolution of our universe. Dark energy is a mysterious force that permeates all of space and drives the accelerating expansion of our universe. Unlike gravity, which pulls objects together, dark energy pushes everything apart. Scientists discovered its existence in the late 1990s when they observed that distant galaxies were moving away from us faster than expected. This enigmatic energy makes up about 68% of the total energy in the observable universe, yet its true nature remains one of the biggest puzzles in modern cosmology. Researchers have proposed various theories to explain dark energy, including the possibility that it is an inherent property of space itself or a new, unknown field that fills the cosmos. Despite its prevalence, dark energy interacts very weakly with ordinary matter and light, making it incredibly difficult to study directly. Its effects can only be observed on the largest cosmic scales, where it overcomes the attractive force of gravity between galaxies and galaxy clusters. Understanding dark energy is crucial for predicting the ultimate fate of our universe. If it continues to dominate, the universe may expand forever, eventually becoming cold and dark as stars burn out and galaxies drift impossibly far apart. This makes dark energy not just a scientific curiosity, but a key to unraveling the cosmic story of our universe's past, present, and future. Dark energy was discovered through meticulous observations of distant supernovae in the late 1990s. Two independent teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were studying these cosmic explosions to measure the expansion rate of the universe. Their expectation was to find that the expansion of the universe was slowing down due to gravity. However, their observations revealed something completely unexpected. The supernovae were fainter than predicted, indicating they were much farther away than anticipated. This meant the universe was not only expanding, but accelerating in its expansion. This acceleration required an unknown force counteracting gravity, pushing the universe apart. This mysterious force was dubbed dark energy. The discovery was so groundbreaking that Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. The finding of dark energy revolutionized our understanding of the cosmos. It showed that about 70% of the universe is composed of this enigmatic energy, fundamentally changing our view of space, time, and the fate of the universe itself. Several lines of evidence support the existence of dark energy, a mysterious force causing the accelerating expansion of our universe. The most compelling evidence comes from observations of distant supernovae. Astronomers discovered that these exploding stars appeared dimmer than expected, indicating they were farther away than calculations based on the known expansion rate of the universe suggested. This unexpected distance implies that the expansion of the universe is accelerating, a phenomenon best explained by the presence of dark energy. The cosmic microwave background, the afterglow of the Big Bang, provides additional support for dark energy. Precise measurements of this ancient light reveal that the universe is flat, meaning its geometry follows the rules of Euclidean geometry. For this to be true, the universe must contain a specific amount of energy. When scientists add up all the visible matter and the theorized dark matter, they fall short of this required amount. Dark energy accounts for this missing energy, making up roughly 68% of the universe's total energy content. Galaxy cluster surveys also lend credence to the dark energy hypothesis. By observing how galaxy clusters have grown and evolved over billions of years, scientists can track the interplay between gravity, which pulls matter together, and the opposing force of dark energy. These observations align with models that include dark energy, further strengthening the case for its existence. Lastly, the distribution of galaxies in the universe, known as the large-scale structure, matches predictions made by models incorporating dark energy. This agreement between theory and observation across multiple independent lines of evidence makes a compelling case for the reality of dark energy, despite our limited understanding of its fundamental nature. Dark energy exerts a profound influence on the expansion of the universe, acting as a mysterious force that pushes space itself apart. Unlike gravity, which pulls matter together, dark energy works in opposition, accelerating the expansion of the cosmos at an ever-increasing rate. This enigmatic form of energy permeates all of space, maintaining a constant density even as the universe expands. As a result, its effects become more dominant over time, overwhelming the attractive force of gravity on the largest cosmic scales. Observations of distant supernovae first revealed this accelerating expansion, leading to the Nobel Prize-winning discovery of dark energy in the late 1990s. The presence of dark energy has significant implications for the fate of the universe. As it continues to drive expansion, Galaxies and galaxy clusters grow more isolated, moving away from each other at faster and faster speeds. In the far future, this could lead to a scenario where most of the observable universe becomes unreachable, with only our local group of galaxies remaining visible. Despite its crucial role in shaping the evolution and destiny of the cosmos, the true nature of dark energy remains one of the biggest mysteries in modern physics. Scientists continue to explore various theories and conduct observations to unravel its secrets, making it a focal point of cutting-edge research in cosmology and fundamental physics. Dark energy plays a crucial role in shaping the ultimate fate of our universe. This mysterious force, which permeates all of space, exerts a repulsive effect that counteracts gravity. As the universe expands, dark energy becomes increasingly dominant, accelerating the expansion at an ever-growing rate. The discovery of dark energy in the late 1990s dramatically changed our understanding of cosmic evolution. Before this revelation, scientists believed the expansion of the universe would eventually slow down due to the gravitational pull of matter. However, observations of distant supernovae showed that the expansion is actually speeding up, pointing to the existence of dark energy. This accelerating expansion has profound implications for the universe's future. If dark energy continues to dominate, the universe will expand forever, growing increasingly cold and empty. This scenario, known as the Big Freeze or heat death, suggests that over vast timescales, stars will burn out, galaxies will be pulled apart, and even atoms may eventually decay, leaving a sparse, dark cosmos. However, the true nature of dark energy remains one of the biggest mysteries in modern physics. If its properties change over time, or it behaves differently than we currently understand, the fate of the universe could be altered. Some theories propose alternative outcomes, such as the Big Rip, where dark energy becomes so powerful it tears apart all structures, from galaxies to atoms. The connection between dark energy and the universe's fate underscores the importance of ongoing research in this field, as it holds the key to understanding our cosmic destiny. Dark energy presents a profound challenge to our understanding of physics, pushing the boundaries of our current scientific knowledge. This mysterious force, which appears to be driving the accelerating expansion of the universe, defies explanation within our established frameworks of physics. One of the most perplexing aspects of dark energy is its apparent uniformity throughout space and time. Unlike other forms of energy we observe, dark energy does not seem to dilute as the universe expands. This behavior contradicts our expectations based on known physical laws and forces us to reconsider fundamental principles of physics. The nature of dark energy also raises questions about the fate of the universe. If dark energy continues to dominate, it could lead to a scenario where the expansion of the universe accelerates indefinitely, potentially resulting in a big rip where even atoms are torn apart. This outcome challenges our understanding of cosmic evolution and the long-term stability of matter itself. Furthermore, the energy density of dark energy observed in the universe is vastly smaller than what quantum field theory predicts for the vacuum energy of space. This discrepancy, known as the cosmological constant problem, highlights a significant gap between quantum mechanics and general relativity, two pillars of modern physics that we have yet to fully reconcile. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have proposed several theories to explain this enigmatic force that appears to be accelerating the expansion of our universe. The leading contender is the cosmological constant, originally proposed by Albert Einstein. This theory suggests that dark energy is an inherent property of space itself, a form of energy density that remains constant as the universe expands. It aligns well with observations, but raises questions about why its value is so small compared to theoretical predictions. Another prominent theory is quintessence, which proposes that dark energy is a dynamic field that varies across time and space. Unlike the cosmological constant, quintessence could potentially explain why the expansion of the universe is accelerating at its current rate. Some researchers explore the possibility that our understanding of gravity might be incomplete. Modified gravity theories suggest that Einstein's general relativity might need revision on cosmic scales, potentially eliminating the need for dark energy altogether. While intriguing, these theories face challenges in explaining all observational data. Time is a fundamental concept in physics, yet its precise definition remains elusive. Physicists generally describe time as a dimension in which events occur in sequence. Unlike the three spatial dimensions we can easily observe, time is often referred to as the fourth dimension, allowing us to pinpoint not just where something happens, but when it happens. In classical physics, time was considered absolute and universal, ticking away at the same rate for everyone and everything in the universe. However, Albert Einstein's theory of relativity revolutionized our understanding of time. According to Einstein, time is relative and can be affected by factors such as gravity and speed. Modern physics views time as part of the fabric of the universe, intimately connected with space in what we call spacetime. This concept suggests that time and space are not separate entities, but are woven together into a single continuum. The flow of time can be distorted by massive objects or high-speed motion, leading to phenomena like time dilation. Despite our increased understanding, the true nature of time remains one of the most profound mysteries in physics. Some theories even suggest that at the most fundamental level, time might not exist as we perceive it, but emerges from more basic quantum processes. As physicists continue to probe the nature of reality, our definition and understanding of time may evolve further. The question of whether time existed before the Big Bang is one of the most profound and challenging in cosmology. Our current understanding suggests that time, as we know it, began with the Big Bang. This event marked the start of our observable universe, and with it, the beginning of space and time themselves. According to the prevailing theories, asking what came before the Big Bang might not be a meaningful question. The concept of before implies a temporal relationship, but if time itself began with the Big Bang, there was no before in any conventional sense. It is akin to asking what is north of the North Pole. The question itself becomes nonsensical at the limit of our understanding. Some theoretical models propose the existence of a state preceding our universe, such as a quantum vacuum or a previous cosmic cycle. However, these ideas remain speculative and beyond our current ability to test or observe. The extreme conditions at the moment of the Big Bang create a barrier to our understanding, as our known laws of physics break down at this singularity. It is important to note that our comprehension of the earliest moments of the universe is still evolving. As we develop new theories and technologies, we may gain fresh insights into the nature of time and the origins of our cosmos. For now, the beginning of time remains intertwined with the birth of our universe in the Big Bang. Time itself is intricately woven into the fabric of our universe, and its relationship with the origin of the cosmos is both profound and perplexing. As we understand it, time as we experience it began at the moment of the Big Bang, approximately 13.8 billion years ago. Before this cosmic event, our current understanding of physics breaks down, and the nature of time becomes unclear. The Big Bang marks the starting point of our observable universe, and with it, the beginning of time as we can measure and comprehend it. This concept challenges our everyday perception of time as a constant, ever-flowing dimension. Instead, cosmologists view time as a fundamental component of spacetime, a four-dimensional continuum that forms the very structure of our universe. In the earliest moments after the Big Bang, time and space were incredibly warped by the extreme energies and densities present. As the universe expanded and cooled, time as we know it began to take shape. This expansion continues today, stretching not just space, but time itself. a phenomenon that becomes particularly apparent when we observe distant galaxies and the cosmic microwave background radiation. The concept of time at the universe's origin also raises questions about what, if anything, came before the Big Bang. Some theories propose cyclical universes or multiverses, but these remain speculative. What we can say with more certainty is that our understanding of time is deeply connected to the birth and evolution of our cosmos, making it an essential aspect of our quest to unravel the mysteries of the universe. The arrow of time is the observed direction of time's flow, always moving forward from the past through the present and into the future. This concept emerges from the fundamental laws of physics, particularly the second law of thermodynamics. In our universe, we observe that events unfold in a specific sequence. We can remember the past, but not the future. Eggs can break, but not unbreak. And hot coffee cools down rather than spontaneously heating up. These everyday observations reflect the arrow of time at work. The key to understanding the arrow of time lies in entropy, a measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This means that, on a cosmic scale, the universe is moving from a more ordered state to a less ordered one. This increase in entropy gives time its apparent direction. It explains why we can distinguish between past and future, and why certain processes appear irreversible. The arrow of time emerges from this fundamental tendency of the universe towards increased entropy, shaping our perception of reality and the unfolding of events in the cosmos. Relativity profoundly shapes our understanding of time in the early universe, revealing a cosmic landscape far different from our everyday experience. In the first moments after the Big Bang, the extreme density and energy of the infant cosmos caused time itself to behave in ways that challenge our intuition. As we peer back toward the beginning of everything, we find that time slowed to a crawl in the incredibly dense early universe. This time dilation, a key aspect of Einstein's theory of relativity, means that what we might perceive as a brief instant actually lasted much longer from the perspective of the primordial particles present then. The fabric of space-time was so warped by the immense gravitational effects that time flowed at a drastically reduced rate. Moreover, relativity tells us that time and space are interwoven, forming a four-dimensional continuum. In the early universe, this space-time was compressed to an extreme degree. As the universe expanded, it stretched not just space, but time itself. This cosmic stretching has profound implications for how we interpret the age and evolution of the universe. Relativity also reveals that our notion of simultaneous events breaks down when we consider the cosmos as a whole. Events that might appear to happen at the same time from one perspective could occur at different times from another. This relativity of simultaneity becomes particularly significant when we attempt to reconstruct the sequence of events in the early universe, reminding us that our earth-bound notions of time are merely a local approximation in the grand cosmic scheme. The nature of time remains one of the most profound and debated questions in physics. In classical physics, time was considered a fundamental aspect of the universe, an absolute backdrop against which events unfolded. However, modern theories have challenged this view, suggesting that time might be an emergent property rather than a fundamental one. Einstein's theory of relativity showed that time is not absolute but relative, intertwined with space in a four-dimensional fabric called spacetime. This revelation hinted at a deeper nature of time, one that depends on the observer's frame of reference and the presence of massive objects. Quantum mechanics further complicated our understanding of time. In some interpretations, time emerges from the interactions of quantum particles and fields. The Wheeler-DeWitt equation, a key component of quantum gravity theories, even suggests a timeless universe at its most fundamental level. Some physicists argue that time is an emergent phenomenon arising from the complex interactions of more fundamental entities in the universe. This view aligns with certain approaches to quantum gravity, where space-time itself is thought to emerge from more basic quantum structures. However, the debate is far from settled, and the true nature of time remains one of the greatest mysteries in modern physics. As we journey back to the earliest moments of our universe, the familiar concept of time begins to unravel. Near the Big Bang, the extreme conditions of temperature, density, and energy create a realm where our standard understanding of physics falters. The very fabric of space-time becomes warped and distorted to such a degree that our usual notions of cause and effect start to lose meaning. In this primordial epoch, quantum effects dominate. The uncertainty principle, a cornerstone of quantum mechanics, suggests that at extremely small scales and high energies, time and energy become intertwined. This leads to fluctuations so rapid and intense that the idea of a smooth, continuous flow of time breaks down. Instead, we enter a domain where time might exist in a state of quantum superposition, simultaneously flowing in multiple directions or perhaps not flowing at all. Moreover, as we approach the Big Bang, the universe becomes incredibly compact. In such a compressed state, gravity becomes so strong that it significantly impacts the nature of time itself. General relativity tells us that gravity can slow time, and near the Big Bang, this effect would be pushed to its limit. Time could slow to a crawl or even come to a complete standstill. This breakdown of time near the Big Bang presents a profound challenge to our understanding of the universe's origins. It suggests that asking what came before the Big Bang might be meaningless, as the very concept of before relies on a conventional understanding of time that may not apply in this extreme regime. The nature of time at the birth of our universe remains one of the most perplexing and fascinating frontiers in modern cosmology. The anthropic principle is a thought-provoking concept in cosmology that addresses the apparent fine-tuning of our universe. It suggests that the fundamental constants and laws of physics seem precisely calibrated to allow for the existence of life as we know it. This principle explores the relationship between the properties of the universe and the emergence of conscious observers like ourselves. At its core, the anthropic principle posits that we observe a universe compatible with our existence because we could not exist to make observations in a universe with different properties. This idea challenges us to consider whether the universe is inherently suited for life or if our presence is merely a consequence of cosmic chance. There are different interpretations of the anthropic principle. The weak anthropic principle simply states that the observed properties of the universe must be compatible with the existence of observers. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Critics argue that the anthropic principle is not scientifically testable and may lead to circular reasoning. Proponents, however, see it as a valuable framework for understanding our place in the cosmos and exploring the fundamental nature of reality. The ongoing debate surrounding this principle continues to fuel discussions about the origins and purpose of our universe. The anthropic principle connects the existence of human life to the fundamental properties of our universe. It suggests that the physical laws and constants we observe are precisely tuned to allow for the emergence of complex life. This principle relates to the origin of the universe by proposing that our universe's initial conditions and subsequent evolution were somehow set up in a way that eventually led to our existence. There are different interpretations of the anthropic principle. The weak version simply states that we observe a universe compatible with our existence because we could not exist to observe it otherwise. The strong version goes further, suggesting that the universe must have properties allowing for observers like us to develop. When applied to the origin of the universe, the anthropic principle raises intriguing questions. Why do fundamental constants like the strength of gravity or the mass of electrons have the exact values they do? If these constants were even slightly different, stars might not form, chemistry as we know it might not exist, and life could be impossible. Some scientists argue that the apparent fine-tuning of our universe might be explained by the existence of multiple universes, each with different physical laws. In this multiverse scenario, we naturally find ourselves in a universe capable of supporting life, while countless others remain lifeless. Others see the anthropic principle as a potential hint at underlying principles yet to be discovered in our quest to understand the origin and nature of our cosmos. The anthropic principle comes in two main forms, the weak version and the strong version. Both attempt to explain why our universe appears perfectly tuned for life, but they approach this question from different angles. The weak anthropic principle states that the conditions we observe in the universe must be compatible with our existence as observers. It suggests that we should not be surprised to find ourselves in a universe that allows life to exist, because we could not observe a universe incompatible with our existence. This version does not make claims about why the universe is the way it is, only that we should expect to observe conditions that allow for our presence. The strong anthropic principle, on the other hand, makes a bolder claim. It proposes that the universe must have properties that allow life to develop within it at some stage in its history. This version suggests that the fundamental constants and laws of physics are somehow constrained to be life-permitting. Some interpretations of the strong anthropic principle even argue that the universe is in some sense designed for life, though this idea remains highly controversial among scientists. While the weak anthropic principle is generally accepted as a logical statement, the strong version is more contentious. Critics argue that the strong anthropic principle makes unfounded assumptions about the nature of the universe and the necessity of life. The debate surrounding these principles continues to spark discussions about the fundamental nature of our cosmos and our place within it. The anthropic principle plays a crucial role in how we understand the fundamental constants of our universe. This principle suggests that the physical laws and constants we observe must be compatible with the existence of conscious life, particularly human life. It proposes that we can only observe a universe that allows for our existence. When we examine universal constants, such as the strength of gravity, the speed of light, or the charge of an electron, we find that they seem incredibly fine-tuned. If these constants were even slightly different, the universe as we know it could not exist. Stars might not form, atoms could be unstable, or matter might not coalesce into larger structures. The anthropic principle offers a perspective on this apparent fine-tuning. It suggests that out of all possible universes with different constants, we naturally find ourselves in one that supports life. This does not necessarily explain why the constants have the values they do, but it does provide a framework for understanding why we observe these specific values. This principle has profound implications for cosmology and our place in the universe. It challenges us to consider whether our universe is unique or part of a vast multiverse where different regions have different physical laws. The anthropic principle reminds us that our very existence as observers influences how we interpret the fundamental nature of reality. The anthropic principle straddles the line between scientific concept and philosophical idea, blending elements of both disciplines. This principle explores the relationship between the existence of intelligent life, particularly humans, and the fundamental properties of the universe. At its core, the anthropic principle suggests that the observable universe must have characteristics that allow for the development of life as we know it. This idea arose from the recognition that many cosmic constants and physical laws seem finely tuned to permit the emergence of complex structures, including stars, planets, and ultimately, living beings. From a scientific perspective, the anthropic principle serves as a framework for understanding why our universe appears so hospitable to life. It has led to testable hypotheses and influenced research in cosmology and particle physics. Scientists use it to explore questions about the nature of our universe and the potential existence of other universes with different physical laws. However, the anthropic principle also ventures into philosophical territory. It raises profound questions about purpose, design, and the place of humanity in the cosmos. Some interpret it as evidence of a purposeful creation, while others view it simply as an observational bias. This philosophical aspect of the principle continues to spark debates about the nature of existence and our understanding of reality. The anthropic principle and the concept of a multiverse are deeply intertwined, offering fascinating perspectives on our existence and the nature of the cosmos. The anthropic principle suggests that the universe appears finely tuned for life because if it were not, we would not be here to observe it. This idea takes on new dimensions when considered alongside the multiverse theory. In the context of a multiverse, our universe might be just one of countless others, each with its own unique set of physical laws and constants. This vast array of universes could explain why our particular cosmos seems so perfectly suited for life. Among the immense number of possible universes, some would inevitably have the right conditions for life to emerge. This connection between the anthropic principle and the multiverse provides a potential solution to the fine-tuning problem in cosmology. Instead of requiring a specific explanation for why our universe has exactly the right properties for life, the multiverse theory suggests that we simply happen to exist in one of the universes where life is possible. However, this idea also raises profound questions about the nature of reality and our place within it. If true, it implies that our universe, despite its vast size, might be just a tiny fraction of a much larger cosmic landscape. This perspective challenges us to reconsider our understanding of the universe and our role as observers within it. The anthropic principle has faced several criticisms from scientists and philosophers alike. One major critique is that it can be seen as a tautology, essentially stating that the universe must be compatible with our existence because we exist to observe it. Critics argue this circular reasoning provides no real explanatory power. Another criticism is that the anthropic principle may lead to lazy thinking or act as a science stopper. By attributing the fine-tuning of universal constants to the necessity of human existence, it could discourage further investigation into the underlying physical mechanisms that actually determine these constants. Some scientists also argue that the principle relies too heavily on our current understanding of physics and biology, which may be incomplete. As our knowledge expands, what we consider necessary conditions for life might change, potentially invalidating some anthropic arguments. Lastly, critics point out that the anthropic principle does not necessarily imply a unique universe tailored for human life. The existence of a multiverse, where our universe is just one of many with different physical constants, could explain our seemingly fine-tuned cosmos without resorting to anthropic reasoning. This multiverse concept challenges the notion that our universe is special or designed specifically for life as we know it. Symmetry in physics is a fundamental concept that describes the unchanging nature of certain aspects of a system under specific transformations. It plays a crucial role in our understanding of the universe and its laws. At its core, symmetry refers to the idea that some properties of a physical system remain constant even when the system undergoes changes or transformations. In the realm of particle physics, symmetries help scientists classify fundamental particles and understand their interactions. For instance, the concept of charge symmetry tells us that the laws of physics would remain the same if we were to swap all particles with their antiparticles. This symmetry provides insights into the behavior of matter and antimatter in the universe. Symmetries also guide physicists in formulating conservation laws, which are cornerstones of our understanding of the physical world. The conservation of energy, for example, arises from the symmetry of time translation, meaning that the laws of physics remain the same regardless of when an experiment is performed. Similarly, the conservation of momentum stems from the symmetry of space translation, indicating that the laws of physics are the same everywhere in space. Understanding symmetries has led to groundbreaking discoveries and predictions in physics. The famous physicist Emmy Noether showed that for every continuous symmetry in nature, there must be a corresponding conserved quantity. This profound connection between symmetries and conservation laws has become a guiding principle in modern physics, helping scientists unravel the mysteries of the cosmos and the fundamental forces that govern it. Symmetry plays a crucial role in our understanding of the fundamental laws of nature. At its core, symmetry in physics refers to the idea that certain aspects of a system remain unchanged when specific transformations are applied. This concept extends far beyond simple geometric shapes and permeates the very fabric of our universe. In particle physics, symmetries guide the behavior of fundamental particles and forces. The Standard Model, our most comprehensive theory of particle physics, is built upon the foundation of symmetry principles. These symmetries dictate how particles interact and transform, leading to the conservation laws that govern the universe. For instance, the conservation of energy stems from the symmetry of time translation, while the conservation of momentum arises from the symmetry of space translation. Perhaps one of the most profound examples of symmetry in nature is the relationship between matter and antimatter. The laws of physics generally treat matter and antimatter equally, showcasing a fundamental symmetry in the universe. However, the observed asymmetry between matter and antimatter in our visible universe remains one of the great mysteries in physics, hinting at potential hidden symmetries or symmetry-breaking mechanisms yet to be fully understood. Symmetry also plays a vital role in our quest for a unified theory of physics. Scientists believe that the seemingly distinct forces of nature may be manifestations of a single, more fundamental force, unified by hidden symmetries that existed in the early universe. As we continue to explore the depths of particle physics and cosmology, symmetry remains a guiding principle, helping us unravel the mysteries of the universe and formulate more comprehensive theories of nature. Symmetry breaking is a fundamental concept in physics that plays a crucial role in our understanding of the early universe. It refers to a process where a system that initially has perfect symmetry transitions to a state with less symmetry. In the context of the early universe, this phenomenon is particularly significant as it helps explain how the universe evolved from its initial, highly uniform state to the complex and diverse cosmos we observe today. In the first moments after the Big Bang, the universe was incredibly hot and dense, with all fundamental forces unified into a single, symmetric state. As the universe expanded and cooled, these forces began to separate, breaking the initial symmetry. This process is similar to how water, which is symmetrical in its liquid form, breaks symmetry as it freezes into ice crystals with distinct patterns and orientations. One of the most important instances of symmetry breaking in the early universe occurred during the electroweak epoch, when the electromagnetic and weak nuclear forces separated. This event, known as electroweak symmetry breaking, gave rise to distinct particles and forces that shape our universe today, including the Higgs boson, which was discovered in 2012. Symmetry-breaking events in the early universe are believed to have led to the creation of matter over antimatter, the formation of galaxies and large-scale structures, and even the emergence of the physical laws that govern our universe. These processes continue to be an active area of research in cosmology and particle physics as scientists strive to unravel the mysteries of our cosmic origins. Supersymmetry is a theoretical framework in particle physics that proposes a fundamental connection between two types of particles, fermions and bosons. This concept attempts to bridge gaps in our understanding of the universe's origin by addressing several key issues in modern physics. At its core, supersymmetry suggests that every known particle has a yet undiscovered partner particle with similar properties but different spin. These hypothetical partner particles could potentially explain the nature of dark matter, which makes up a significant portion of the universe but remains elusive to direct observation. Moreover, supersymmetry offers a potential solution to the hierarchy problem in particle physics, which questions why gravity is so much weaker than the other fundamental forces. By introducing partner particles, supersymmetry could help stabilize the mass of the Higgs boson, a crucial component in our understanding of how particles acquire mass. Perhaps most intriguingly, supersymmetry plays a role in string theory, a candidate for a unified theory of everything. In this context, it helps reconcile quantum mechanics and general relativity, two foundational but seemingly incompatible theories describing the universe at different scales. While supersymmetry remains unproven, its potential to explain fundamental aspects of our universe continues to drive research and shape our understanding of cosmic origins. Symmetry plays a crucial role in our understanding of the fundamental forces that govern the universe. At the most basic level, symmetry in physics refers to the idea that certain properties of a system remain unchanged under specific transformations. This concept has proven invaluable in unifying our understanding of seemingly disparate forces. The Standard Model of particle physics, which describes three of the four fundamental forces, electromagnetic, weak, and strong nuclear forces, is built upon the principle of gauge symmetry. This mathematical framework allows physicists to describe these forces in a unified manner, revealing their underlying similarities despite their apparent differences in everyday observations. One of the most significant triumphs of symmetry in physics was the unification of electricity and magnetism into the electromagnetic force by James Clerk Maxwell in the 19th century. This unification showed that these two seemingly separate phenomena were actually different aspects of the same fundamental interaction, governed by a set of equations that remain unchanged under certain symmetry transformations. The quest for further unification continues, with many physicists seeking a grand unified theory that would bring together all fundamental forces, including gravity, under a single symmetry principle. While this goal remains elusive, the success of symmetry in past unifications gives scientists hope that it may hold the key to a deeper understanding of the universe's most fundamental workings. Symmetry plays a fundamental role in particle physics and the Standard Model, shaping our understanding of the universe's most basic components. At its core, symmetry in physics refers to the idea that certain aspects of a system remain unchanged under specific transformations. This concept has profound implications for the behavior and properties of subatomic particles. In the Standard Model, three key symmetries govern particle interactions: charge conjugation, parity, and time reversal. These symmetries, collectively known as CPT symmetry, provide a framework for understanding how particles and their antiparticles behave. For instance, charge conjugation symmetry suggests that the laws of physics should remain the same if we swap all particles with their antiparticles. Symmetries also help explain the existence and properties of fundamental forces. The electromagnetic force, for example, arises from a symmetry called gauge invariance. This symmetry principle led to the development of quantum electrodynamics, which describes how light and matter interact. Similarly, the weak and strong nuclear forces are understood through symmetry principles, unifying our comprehension of particle interactions. Perhaps most importantly, symmetry breaking mechanisms in the early universe are thought to be responsible for the existence of matter as we know it. The slight imbalance between matter and antimatter, crucial for our universe's structure, is believed to have resulted from a subtle violation of certain symmetries during the universe's infancy. This demonstrates how symmetry and its occasional violation shapes the very fabric of reality studied in particle physics. Symmetry principles play a crucial role in our understanding of the universe's origins. These fundamental concepts suggest that the universe may have emerged from a state of perfect balance or nothingness. In this scenario, the total energy of the universe would be zero, with matter and antimatter, positive and negative energies, perfectly cancelling each other out. Quantum fluctuations, governed by the uncertainty principle, could have disrupted this perfect symmetry, leading to the rapid expansion we call inflation. This process would have created the matter and energy we observe today while still maintaining an overall balance. The idea that something can come from nothing is counterintuitive, but it aligns with our current understanding of quantum mechanics and cosmology. Symmetry breaking, a process where the universe transitions from a highly symmetric state to one with less symmetry, could explain how the fundamental forces of nature separated and how particles acquired mass. This concept helps bridge the gap between the seemingly impossible emergence of everything from nothing and the complex universe we observe today. While these ideas are still theoretical, they demonstrate how symmetry principles provide a framework for understanding the universe's beginnings without violating conservation laws. As we continue to explore these concepts, we may uncover deeper insights into the nature of reality and the origins of our cosmos. Quantum gravity represents one of the most challenging frontiers in modern physics. It aims to reconcile two fundamental theories that describe our universe: quantum mechanics and general relativity. Quantum mechanics explains the behavior of particles at the smallest scales, while general relativity describes gravity and the structure of spacetime at cosmic scales. The need for quantum gravity arises because these two theories, despite their individual successes, are incompatible in extreme conditions, such as inside black holes or during the earliest moments of the universe. Scientists believe that at these extreme scales, gravity must behave according to quantum principles, just like the other fundamental forces of nature. Various approaches to quantum gravity have been proposed. String theory suggests that all particles and forces, including gravity, arise from tiny vibrating strings in multiple dimensions. Loop quantum gravity, another prominent theory, proposes that space itself is composed of discrete units at the smallest scales. Despite decades of research, a complete theory of quantum gravity remains elusive. Its development could revolutionize our understanding of the universe, potentially explaining the nature of dark energy, the origin of the cosmos, and the ultimate fate of black holes. The quest for quantum gravity continues to drive theoretical physics forward, pushing the boundaries of human knowledge about the fundamental nature of reality. Understanding the universe's origin requires a theory of quantum gravity because our current models of physics break down when describing the extreme conditions of the early universe. General relativity, which explains gravity on large scales, and quantum mechanics, which governs the behavior of particles at tiny scales, are incompatible in their current forms. This incompatibility becomes problematic when we try to describe the intense gravitational effects and minuscule scale of the universe at its birth. The moment of the Big Bang represents a singularity where the laws of physics as we know them cease to function. At this point, the universe was incredibly dense and hot, with all its mass compressed into a space smaller than an atom. In such extreme conditions, quantum effects and gravitational forces were both significant, requiring a unified theory to explain their interaction. A theory of quantum gravity would bridge the gap between these two fundamental theories, providing a framework to understand how gravity behaves at the quantum scale. This unified approach is crucial for explaining phenomena like the initial expansion of the universe, the formation of cosmic structures, and the nature of black holes. Moreover, a quantum theory of gravity might help resolve other mysteries, such as the nature of dark energy and dark matter, or explain why gravity is so much weaker than the other fundamental forces. By providing a more complete picture of the universe's fundamental workings, it would allow scientists to trace cosmic history back to its very first moments, offering unprecedented insights into the origin and evolution of our universe. Scientists have been working for decades to unify quantum mechanics and general relativity into a single, comprehensive theory of quantum gravity. Several promising approaches have emerged, each with its own strengths and challenges. String theory is one of the most well-known contenders. It proposes that all matter and energy in the universe are composed of tiny, vibrating strings. These strings exist in multiple dimensions beyond the four we can observe, potentially explaining gravity as a consequence of how these strings interact across higher dimensions. Loop quantum gravity offers a different perspective, suggesting that space itself is quantized into discrete units at the smallest scales. This approach aims to describe gravity using the same quantum framework applied to other fundamental forces, without the need for extra dimensions or strings. Another avenue of research is causal dynamical triangulations, which attempts to build spacetime from the ground up using simple geometric elements. This approach has shown promise in reproducing some features of our four-dimensional universe in computer simulations. Additionally, theories like asymptotic safety and causal sets are being explored, each offering unique insights into how gravity might behave at the quantum scale. Quantum gravity represents a frontier in physics, aiming to unite quantum mechanics with general relativity. This theoretical framework could potentially explain how space and time emerge from more fundamental quantum processes. At the smallest scales, quantum gravity suggests that space and time might not be smooth and continuous as we perceive them, but rather composed of discrete units, sometimes called space-time atoms. These fundamental building blocks could combine and interact according to quantum principles, giving rise to the fabric of space-time we experience. One intriguing concept in quantum gravity is the idea of entanglement as a creator of space-time. Just as quantum entanglement links particles across distances, it might also weave together the very structure of the universe. This notion proposes that the intricate network of quantum connections between these space-time atoms could be what we interpret as the continuum of space and time. Furthermore, quantum gravity theories often suggest that time itself might emerge from quantum fluctuations in a timeless realm. This challenges our conventional understanding of cause and effect, hinting at a more complex and interconnected universe where space and time are not fundamental, but rather consequences of deeper quantum phenomena. Loop quantum gravity is a theoretical framework that attempts to merge quantum mechanics with Einstein's theory of general relativity. It proposes that space itself is composed of tiny, discrete units, much like the pixels on a digital screen. These fundamental units of space, often called atoms of spacetime, form a complex network of interconnected loops and nodes. When applied to the early universe, loop quantum gravity offers a fascinating alternative to the traditional Big Bang theory. Instead of an infinitely dense singularity, this model suggests a big bounce. In this scenario, our universe may have emerged from the collapse of a previous universe, bouncing back in a cyclical process. The theory predicts that as matter becomes extremely dense, gravity begins to repel rather than attract. This repulsive force prevents the formation of a singularity and instead causes the universe to rebound, expanding outward once again. This process could potentially repeat indefinitely, creating a series of expanding and contracting universes. Loop quantum gravity also addresses the problem of the initial singularity in classical cosmology. By describing space and time as discrete rather than continuous, it avoids the mathematical infinities that plague other theories when describing the moment of the Big Bang. This approach provides a potential bridge between the quantum world and the large-scale structure of the universe, offering new insights into the nature of space, time, and the origins of our cosmos. String theory proposes a revolutionary approach to understanding the fundamental nature of the universe. It seeks to bridge the gap between quantum mechanics, which describes the behavior of subatomic particles, and gravity, which governs the interactions of large-scale objects. At its core, string theory suggests that the basic building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings are incredibly small, measuring about 100 billion times smaller than an atomic nucleus. According to the theory, different vibrations of these strings give rise to all the particles and forces we observe in nature, including gravity. This concept offers a potential solution to the long-standing conflict between quantum mechanics and general relativity. In the string theory framework, gravity emerges naturally as a consequence of string vibrations, just like other fundamental forces. This unified approach could potentially explain how gravity operates at the quantum scale, a puzzle that has eluded physicists for decades. However, string theory remains highly speculative and unproven. It requires the existence of extra dimensions beyond the four we experience in everyday life. These additional dimensions are thought to be tightly curled up and invisible to our current methods of observation, presenting significant challenges for experimental verification. Observational evidence for quantum gravity remains elusive, but scientists are pursuing several promising avenues. One potential source of evidence could come from studying gravitational waves produced by extreme cosmic events. These ripples in space-time might carry subtle imprints of quantum effects that could be detected by increasingly sensitive instruments. Another area of interest is the cosmic microwave background radiation, the afterglow of the Big Bang. Some theories of quantum gravity predict specific patterns or anomalies in this radiation that could be observed with advanced telescopes. Scientists are also examining high-energy cosmic rays, as quantum gravity effects might influence how these particles behave over vast cosmic distances. Black holes present another intriguing opportunity for observing quantum gravity. The intense gravitational fields near black holes could potentially reveal quantum effects, particularly in the behavior of matter and energy at the event horizon. Some researchers propose that Hawking radiation, a theoretical quantum effect near black holes, could provide indirect evidence of quantum gravity if detected. Experiments on Earth, while challenging, might also contribute to our understanding. Precision measurements of gravity at extremely small scales or in highly controlled quantum systems could potentially reveal deviations from classical gravitational theory, hinting at quantum gravitational effects. As technology advances, these various approaches may converge to provide the observational evidence needed to support or refute theories of quantum gravity. Our quest to comprehend the universe's origin pushes the boundaries of human knowledge and scientific capability. While we have made remarkable strides in understanding cosmic evolution, fundamental limits constrain our ability to peer back to the very beginning. The cosmic microwave background radiation, a faint afterglow of the early universe, provides our earliest glimpse of cosmic history, dating back to about 380,000 years after the Big Bang. However, the period before this remains shrouded in mystery, hidden behind a veil of intense heat and density that obscures our view. Theoretical physics suggests that quantum effects dominated the universe in its earliest moments, but our current theories break down when describing these extreme conditions. The marriage of quantum mechanics and general relativity, necessary for understanding the birth of the universe, remains elusive despite decades of scientific effort. Moreover, our observational tools have physical limitations. Even the most advanced telescopes and detectors cannot directly observe the universe's first moments. As we approach the limits of what our current technology can reveal, we find ourselves facing the humbling reality that some aspects of cosmic origins may forever remain beyond our grasp. Technological limitations significantly impact our ability to study the early universe. Our most powerful telescopes and instruments, while incredibly advanced, still face challenges when peering back to the dawn of time. The farther we look into space, the further back in time we see, but the light from the earliest moments of the universe is incredibly faint and difficult to detect. One major hurdle is the cosmic microwave background radiation, which acts like a wall, blocking our view of anything that happened before about 380,000 years after the Big Bang. This radiation, while invaluable for understanding the early universe, also limits how far back we can directly observe. Another challenge lies in detecting and studying the first stars and galaxies. These objects are extremely distant and faint, pushing the limits of our current telescope technology. Even our most advanced space-based observatories struggle to capture clear images or spectra from these ancient celestial bodies. Furthermore, our understanding of particle physics at the extreme energies present in the early universe is incomplete. This limits our ability to model and interpret the processes that occurred in those first moments after the Big Bang. As we continue to advance our technology and refine our theories, we hope to overcome these limitations and gain a clearer picture of the universe's earliest epochs. The cosmic horizon represents the farthest distance we can see in the observable universe. This boundary exists because of the finite speed of light and the age of the universe. Light from objects beyond this horizon simply hasn't had enough time to reach us since the Big Bang occurred approximately 13.8 billion years ago. This cosmic horizon effectively limits our observations by creating a sphere around us, beyond which we cannot detect or measure anything directly. The actual universe likely extends far beyond this observable limit, but we are fundamentally unable to gather information from those distant regions. Interestingly, the cosmic horizon is not a fixed boundary. As the universe continues to expand, light from increasingly distant objects eventually reaches us, gradually pushing our cosmic horizon outward. However, due to the accelerating expansion of the universe, there are regions we will never be able to observe, no matter how long we wait. The concept of the cosmic horizon reminds us that our view of the universe is inherently limited. It underscores the vast scale of the cosmos and the challenges we face in understanding its true extent and nature. Our quest to understand the universe's beginning faces significant challenges. The extreme conditions of the early universe push our theories to their limits, making it difficult to test and verify our ideas. The cosmic microwave background radiation, the oldest light we can observe, only shows us the universe about 380,000 years after the Big Bang. This leaves us with a cosmic blind spot for the earliest moments of our universe's existence. The concept of cosmic inflation, a period of rapid expansion in the first fraction of a second after the Big Bang, further complicates our understanding. While inflation explains many observed features of our universe, it also suggests the possibility of a multiverse, a concept that might be inherently untestable from within our own universe. Quantum mechanics and general relativity, our two most successful physical theories, break down when describing the extreme conditions of the very early universe. Scientists are still working to develop a unified theory of quantum gravity that could potentially describe these earliest moments. However, even if such a theory is developed, we may face fundamental limits in our ability to test its predictions about the universe's beginning. Moreover, the question of what came before the Big Bang may be meaningless from a scientific perspective. If time itself began with the Big Bang, as some theories suggest, then asking what came before might be like asking what's north of the North Pole. These conceptual and observational limits highlight the profound challenges we face in our quest to fully understand the universe's origins. Philosophical considerations play a crucial role in shaping our understanding of cosmic origins, bridging the gap between scientific observations and the profound questions of existence. These reflections challenge us to think beyond the purely empirical and consider the deeper implications of our discoveries about the universe. One key philosophical aspect is the question of causality. As we trace the history of the cosmos back to its earliest moments, we encounter the limits of our current scientific models. This leads to the age-old inquiry: what caused the universe to come into being? The concept of a first cause or an uncaused cause has been debated by philosophers for millennia and continues to influence how we interpret the Big Bang theory. Another important philosophical consideration is the anthropic principle, which suggests that the universe must have properties that allow for the development of conscious life to observe it. This idea raises questions about the apparent fine-tuning of cosmic constants and whether our universe is unique or part of a larger multiverse. Such reflections push us to consider the relationship between observers and the observed universe, challenging our notions of objectivity and the nature of scientific inquiry itself. Philosophical thinking also encourages us to examine the limits of human knowledge and the nature of explanation. As we strive to understand cosmic origins, we must grapple with concepts that seem to defy intuition, such as the nature of time before the Big Bang or the possibility of infinite universes. These considerations remind us that our quest to understand the cosmos is not just a scientific endeavor, but a deeply human one, intertwining our desire for knowledge with our search for meaning and place in the universe. Mathematics serves as the fundamental language for describing and understanding the origin of the universe. It provides a precise framework that allows scientists to model complex cosmic phenomena and make predictions about the early moments of our universe's existence. In the context of the Big Bang theory, mathematical equations derived from Einstein's theory of general relativity describe how space and time themselves came into being. These equations enable cosmologists to trace the universe's expansion backward, approaching the singular point from which everything emerged. Quantum mechanics, another mathematical framework, becomes crucial when exploring the universe at its smallest scales and earliest moments. It helps scientists understand the behavior of subatomic particles and the forces that govern the infant universe, providing insights into how matter and energy interacted in those first fractions of a second. Mathematical models also play a vital role in explaining cosmic inflation, the theory that the universe underwent a period of rapid expansion shortly after its birth. These models help scientists reconcile observations of the current universe with theoretical predictions, offering explanations for its uniformity and structure on large scales. Future discoveries have the potential to revolutionize our understanding of cosmic origins in profound ways. As technology advances and new observational techniques emerge, scientists may uncover evidence that challenges or refines our current models of the universe's birth and evolution. One area ripe for groundbreaking discoveries is the nature of dark matter and dark energy. These mysterious components make up the majority of the universe's content, yet their true nature remains elusive. Future experiments and observations could reveal the properties of dark matter particles or uncover new physics that explains dark energy, potentially rewriting our understanding of how the cosmos formed and grew. Advancements in gravitational wave astronomy might allow us to peer further back in time, possibly even to the first fractions of a second after the Big Bang. This could provide direct evidence of cosmic inflation or reveal unexpected phenomena from the universe's earliest moments. Additionally, improved observations of the cosmic microwave background radiation might uncover subtle patterns that shed new light on the conditions present in the infant universe. Discoveries in particle physics, such as at upgraded particle accelerators, could reveal new fundamental particles or forces that played crucial roles in the early universe. These findings might necessitate revisions to our models of how matter and energy behaved in the extreme conditions following the Big Bang, potentially altering our entire conception of cosmic origins. The origin of the universe has profoundly influenced philosophical thought, challenging our understanding of existence and our place within it. The idea that everything we know had a beginning forces us to grapple with questions of causality and purpose on a cosmic scale. Many philosophers have pondered whether the universe's origin implies a creator, or if it arose from natural processes. This debate has shaped religious and secular worldviews alike, influencing how we perceive the nature of reality and our own significance within it. The concept of a finite universe with a definite starting point also raises questions about time itself. Philosophers and scientists alike have wrestled with the notion of what came before the universe began, leading to complex discussions about the nature of time and causality. Furthermore, our growing understanding of the universe's origin has impacted how we view human existence. The realization that we are made of elements forged in stars billions of years ago connects us intimately to the cosmos, prompting philosophical reflections on our relationship with the universe and our role in its ongoing story. The idea of a universe arising from nothing challenges our fundamental understanding of causality. This concept, rooted in quantum physics and theoretical cosmology, suggests that the universe could have spontaneously emerged without a prior cause or pre-existing conditions. In classical physics, every effect has a cause, forming a chain of events that can be traced back in time. However, at the quantum level, particles can appear and disappear in the vacuum of space, seemingly violating this principle. Some physicists propose that our entire universe might have originated through a similar process, but on a cosmic scale. This notion disrupts our intuitive understanding of cause and effect, forcing us to reconsider the nature of time and the beginning of existence itself. If the universe truly came from nothing, it implies that there was no before the universe, as time itself began with the universe's creation. This idea challenges our concept of infinite regress and the need for a first cause. Moreover, a universe from nothing raises questions about the role of physical laws. Did these laws exist before the universe, guiding its creation? Or did they emerge with the universe itself? These puzzles push the boundaries of our understanding, inviting us to explore new paradigms of causality and existence. The concept of cosmic origins touches on fundamental questions that have intrigued humanity for millennia. As we explore the vast expanse of the universe and uncover its history, we naturally find ourselves pondering our place within it. The Big Bang Theory, which describes the beginning of our universe roughly 13.8 billion years ago, provides a scientific framework for understanding our cosmic origins. Yet this knowledge often leads to deeper philosophical inquiries about purpose and meaning. When we consider that all matter in the universe, including the atoms in our bodies, originated from this primordial event, it can evoke a sense of connection to the cosmos. This realization that we are made of star stuff, as Carl Sagan famously noted, can inspire awe and wonder. It suggests that our existence is intimately tied to the grand cosmic narrative, potentially imbuing our lives with a sense of significance on a universal scale. However, the scientific understanding of our origins does not inherently provide answers to questions of purpose or meaning. These are largely philosophical and personal matters that extend beyond the realm of empirical observation. Some find that the vastness of the cosmos and our place within it underscore the preciousness of human existence, while others may view it as highlighting our cosmic insignificance. Ultimately, the relationship between cosmic origins and questions of purpose and meaning is complex and multifaceted. While science can inform our understanding of how the universe and life came to be, the interpretation of this knowledge and its implications for our lives remain deeply personal. The exploration of our cosmic origins continues to fuel both scientific inquiry and philosophical contemplation, driving us to seek a deeper understanding of our place in the universe. The concept of an eternal universe presents profound philosophical challenges that have intrigued thinkers for centuries. One fundamental question it raises is the nature of causality itself. If the universe has always existed without a beginning, it challenges our understanding of cause and effect. This leads to the perplexing idea of an infinite regression of causes, where each event is caused by a previous one, stretching back eternally. Another challenge lies in reconciling the idea of an eternal universe with the concept of time. Our conventional understanding of time often includes a starting point, but an eternal universe suggests time itself might be infinite. This notion forces us to reconsider our perception of past, present, and future, and whether these distinctions hold meaning in an eternal cosmos. The concept also raises questions about the purpose and meaning of existence. In a universe without a beginning or end, traditional notions of cosmic purpose or divine creation are challenged. This leads to philosophical debates about the nature of existence itself and whether meaning can be found in an eternal, unchanging reality. Furthermore, an eternal universe confronts us with the idea of infinite possibilities. Given infinite time, would every possible event eventually occur? This concept, known as the infinite monkey theorem, suggests that in an eternal universe, even the most improbable events would happen, not just once, but infinitely many times. This challenges our understanding of probability, uniqueness, and the significance of individual events in the grand cosmic scale. Across human history, diverse cultures and religions have developed unique interpretations of how the universe came into being. Many ancient civilizations saw the universe as emerging from primordial chaos or darkness. The ancient Egyptians believed that the god Atum created the universe by rising from the waters of chaos. In Norse mythology, the cosmos formed from the void called Ginnungagap, with ice and fire playing crucial roles in its creation. Abrahamic religions such as Judaism, Christianity, and Islam share a common narrative of divine creation, where an omnipotent God brought the universe into existence. The book of Genesis describes this process occurring over 6 days, with God creating light, the heavens, earth, celestial bodies, plants, animals, and finally, humans. Hinduism presents a cyclical view of the universe, with periods of creation, preservation, and destruction repeating endlessly. The god Brahma is often associated with the creation aspect of this cycle. Eastern philosophies offer different perspectives. Buddhism, for instance, does not focus on a specific creation event, but instead emphasizes the concept of dependent origination, where all phenomena arise from interconnected causes and conditions. Taoism speaks of the Tao as the source of all existence, describing it as an ineffable force that gives rise to the universe through a process of spontaneous emergence. Scientific cosmology, while not a religious or cultural interpretation, has become influential in modern times. The Big Bang theory, which proposes that the universe expanded from an incredibly dense and hot state about 13.8 billion years ago, has gained widespread acceptance among scientists. This theory, based on observational evidence and mathematical models, offers a stark contrast to many traditional creation myths, illustrating how our understanding of the universe continues to evolve. Our growing understanding of cosmic origins raises profound ethical questions that challenge our place in the universe. As we uncover the vast scales of space and time involved in the formation of our cosmos, we are confronted with the realization of our own cosmic insignificance. This knowledge compels us to reevaluate our responsibilities and priorities as a species. The discovery that we are made of star stuff forged in the hearts of ancient suns connects us intimately to the cosmos. This shared atomic heritage with all matter in the universe implies a fundamental unity that transcends earthly boundaries. It raises questions about our obligations to preserve and protect not just our own planet, but the cosmic environment as a whole. Our understanding of the rarity of conditions that allow for life as we know it also brings ethical considerations. If we are indeed rare in the cosmos, does this imbue us with a special responsibility as conscious observers of the universe? Some argue this knowledge should motivate us to become stewards of life, working to ensure its continuation and spread beyond Earth. Conversely, the possibility of widespread life in the universe raises ethical questions about our interactions with potential extraterrestrial civilizations. How do we balance the pursuit of knowledge through exploration with the need to respect and preserve any life we might encounter? These questions challenge us to develop ethical frameworks that extend beyond our planet, preparing us for a future as a spacefaring civilization. Our understanding of the universe's beginning profoundly shapes our perspective on human significance. The Big Bang theory, which describes the origin of our universe roughly 13.8 billion years ago, reveals a cosmic history far grander and more ancient than humanity's brief existence. This vast timescale and the enormous scale of the cosmos can make our species seem insignificant at first glance. However, our ability to comprehend and study these cosmic origins speaks to the remarkable capabilities of the human mind. We are, in a sense, the universe becoming aware of itself. Our scientific discoveries about the early universe, from the initial expansion to the formation of the first stars and galaxies, showcase our intellectual reach beyond our immediate surroundings. Moreover, Our understanding of the universe's beginning highlights the rarity and preciousness of life. The delicate balance of conditions necessary for life to emerge and evolve underscores the uniqueness of our existence. This realization can foster a sense of responsibility to preserve and cherish life on Earth, our only known haven in the cosmos. Ultimately, our cosmic origin story connects us to the universe in a profound way. We are made of star stuff, forged in the hearts of long-dead stars. This shared heritage with the cosmos can inspire a sense of wonder and unity, reminding us that we are an integral part of the universe's ongoing story. The future evolution of the universe is a topic of intense study and speculation among cosmologists. Based on our current understanding, the universe is expected to continue expanding at an accelerating rate, driven by the mysterious force we call dark energy. This expansion will cause galaxies to move farther apart, making the night sky appear increasingly empty over vast timescales. As stars exhaust their fuel, new star formation will gradually slow down and eventually cease. The universe will enter a phase known as the degenerate era, lasting for trillions of years. During this time, smaller stars will fade and die, while larger ones may explode as supernovae or collapse into black holes. The remaining stellar remnants, such as white dwarfs, neutron stars, and black holes, will dominate the cosmos. Even these remnants are not eternal. Over unimaginably long periods, protons may decay and black holes could evaporate through Hawking radiation. This could lead to the black hole era, where massive black holes become the primary structures in the universe. Eventually, even these might disappear, leaving a nearly empty, cold universe in a state cosmologists call the dark era. However, it is important to note that these predictions are based on our current knowledge, which is still evolving. New discoveries or a better understanding of dark energy and other cosmic phenomena could significantly alter our vision of the far future of the universe. The ultimate fate of our universe remains one of the most intriguing questions in cosmology. Scientists have proposed several scenarios, each based on our current understanding of physics and observations of the cosmos. One possibility is the Big Freeze, also known as heat death. In this scenario, the universe continues to expand forever, growing increasingly cold and sparse. Stars exhaust their fuel, galaxies drift apart, and eventually all matter decays into low-energy particles, leaving a vast, dark, and essentially empty universe. Another potential outcome is the Big Crunch. This theory suggests that the expansion of the universe might eventually slow down and reverse. Gravity would then pull everything back together, culminating in a hot, dense state similar to the one that preceded the Big Bang. A third scenario, called the Big Rip, proposes a more dramatic end. If dark energy, the mysterious force driving the universe's acceleration, continues to grow stronger, it could eventually overcome all other forces. This would tear apart galaxies, stars, planets, and even atoms, ripping the very fabric of space-time itself. Dark energy plays a crucial role in shaping our understanding of the universe's future. This mysterious force, which makes up about 70% of the universe's total energy content, is responsible for the accelerating expansion of space itself. As we look ahead, dark energy's influence becomes increasingly significant, fundamentally altering our predictions about cosmic evolution. In the coming billions of years, dark energy is expected to drive galaxies and galaxy clusters farther apart at an ever-increasing rate. This relentless expansion will eventually isolate most galaxies from one another, making them appear to recede faster than the speed of light from an observer's perspective. The result will be a universe where distant galaxies fade from view, leaving each galaxy cluster alone in a vast, dark cosmos. This accelerating expansion also has profound implications for the ultimate fate of the universe. If dark energy maintains its current properties, the universe might experience a Big Freeze scenario. In this future, the universe continues to expand indefinitely, cooling as it grows, until it reaches a state of maximum entropy. Stars will exhaust their fuel, black holes will evaporate, and the universe will become an increasingly cold and empty place. However, our understanding of dark energy is still limited, and its nature could change over time. If dark energy were to become even more powerful, it could lead to a more dramatic end, known as the Big Rip, where the fabric of space-time itself is torn apart. Conversely, if dark energy weakens, the universe's expansion could slow or even reverse, potentially leading to a big crunch, where all matter collapses back into a singularity. These possibilities underscore the critical role dark energy plays in determining the ultimate destiny of our universe. The heat death of the universe is the ultimate fate that many scientists believe awaits our cosmos. This concept describes a future state where the universe has expanded to such an extent that it reaches maximum entropy. In this scenario, all energy becomes evenly distributed throughout space, making it impossible for any useful work to be performed. As the universe continues to expand, stars will eventually exhaust their fuel and burn out. Galaxies will drift apart, and black holes will slowly evaporate through Hawking radiation. Over unimaginably long timescales, all matter will break down, leaving behind a vast, cold expanse filled with elementary particles. In this final state, the universe would be incredibly dark and cold, approaching absolute zero in temperature. No complex structures would exist, and no processes could occur that would distinguish the past from the future. The universe would essentially reach a state of perfect equilibrium where nothing of significance happens. This concept of heat death stems from the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. The universe, being a closed system, is subject to this law, leading to the conclusion that it will eventually reach a state of maximum disorder and uniformity. The possibility of another Big Bang-like event occurring in our universe is a topic of intense speculation among cosmologists. Current theories suggest that our universe is expanding at an accelerating rate, driven by a mysterious force called dark energy. This expansion is expected to continue indefinitely, making a scenario similar to the Big Bang unlikely in our observable universe. However, some hypotheses propose the concept of a cyclic universe, where periods of expansion are followed by contraction, potentially leading to a big crunch that could trigger another Big Bang. This idea, while intriguing, lacks substantial evidence and remains highly speculative. Another perspective comes from the multiverse theory, which suggests that our universe might be one of many. In this scenario, other universes could potentially experience their own Big Bang events, though these would be separate from and unobservable to us. It is important to note that our understanding of the universe is continually evolving. Future discoveries in physics and cosmology may reshape our views on the fate of the universe and the possibility of cosmic rebirth. For now, based on current observations, another Big Bang-like event within our observable universe seems improbable. The concept of cyclic universes offers an intriguing alternative to the traditional view of our universe's fate. While many cosmologists believe our universe will expand indefinitely, eventually succumbing to heat death, the cyclic model proposes a different scenario. In this view, our universe undergoes endless cycles of expansion and contraction. According to this theory, our current universe is just one in a series of universes that have existed and will exist. Each universe expands, reaches a maximum size, then contracts back to a singularity before exploding outward again in a new Big Bang. This process repeats indefinitely, creating a never-ending cycle of death and rebirth on a cosmic scale. One fascinating aspect of the cyclic universe model is its implication for the arrow of time. In our observable universe, time appears to flow in one direction. However, in a cyclic universe, the concept of a beginning or end becomes meaningless. Each cycle could potentially have its own arrow of time, reversing with each new iteration. The cyclic universe theory also addresses some puzzling aspects of our current cosmological models, such as the nature of dark energy and the apparent fine-tuning of physical constants. It suggests that these properties might be inherited or evolved from previous cycles, potentially explaining their current values without resorting to concepts like the multiverse. The future of the universe holds profound implications for our understanding of its origin. As we peer into the cosmic horizon, we find that the universe's destiny is intricately linked to its birth. The ongoing expansion of space, first discovered by Edwin Hubble, continues to shape the cosmos. This expansion, which began with the Big Bang, is now known to be accelerating due to the mysterious force we call dark energy. This acceleration poses a fascinating question about the universe's beginning. If the expansion continues indefinitely, it suggests that the universe might have emerged from an infinitely dense point, supporting the Big Bang theory. However, some scientists propose alternative models, such as the idea of a cyclic universe that expands and contracts over immense timescales. The ultimate fate of the universe also informs our view of its origin. If the universe ends in a big freeze, with all matter and energy spread thin across vast distances, it implies a universe that began in a highly ordered, low-entropy state. Conversely, if the universe ends in a big crunch, collapsing back in on itself, it might suggest a cyclical nature to cosmic evolution, challenging our current models of the Big Bang. Furthermore, the discovery of cosmic inflation, a period of rapid expansion in the early universe, has reshaped our understanding of cosmic origins. This inflationary period explains the remarkable uniformity we observe across vast cosmic distances, providing a link between the universe's past and its future evolution. As we continue to study the cosmos, each new insight into its future helps us refine and sometimes revolutionize our theories about how it all began. Our exploration of the early universe relies on a range of sophisticated technologies that push the boundaries of human ingenuity. Radio telescopes play a crucial role, capturing faint signals from the cosmos that have traveled for billions of years. These massive instruments, like the Atacama Large Millimeter Array in Chile, detect radio waves emitted by ancient galaxies and the afterglow of the Big Bang itself. Space-based observatories have revolutionized our understanding of the early universe. The Hubble Space Telescope, orbiting high above Earth's atmosphere, has peered deep into space and time, revealing galaxies as they appeared billions of years ago. Its successor, the James Webb Space Telescope, uses advanced infrared technology to observe even fainter, more distant objects from the universe's infancy. Particle accelerators, like the Large Hadron Collider, also contribute to our knowledge of cosmic origins. By smashing particles together at nearly the speed of light, scientists recreate conditions similar to those moments after the Big Bang, offering insights into the fundamental forces and particles that shaped our universe. Computer simulations and data analysis tools are equally vital. Powerful supercomputers process vast amounts of observational data and model complex cosmic phenomena, allowing scientists to test theories about the early universe and make predictions for future observations. These technologies work in concert, each providing a unique piece of the cosmic puzzle as we strive to understand our universal origins. Space-based telescopes have revolutionized our understanding of cosmic origins by providing unparalleled views of the universe. These advanced instruments, orbiting high above Earth's atmosphere, capture light from the farthest reaches of space and time. Unlike ground-based telescopes, space telescopes avoid atmospheric distortion and can detect a wider range of electromagnetic radiation. This capability allows astronomers to observe phenomena invisible from Earth, such as the cosmic microwave background radiation, a faint glow left over from the Big Bang. By studying this ancient light, scientists have gained crucial insights into the early universe and its expansion. Space telescopes also excel at detecting faint, distant galaxies formed shortly after the Big Bang. These observations help cosmologists piece together the universe's evolutionary timeline, from the first stars and galaxies to the complex structures we see today. Additionally, by analyzing the chemical composition of these early cosmic objects, researchers can trace the origin and distribution of elements throughout the universe's history. Furthermore, space-based instruments have played a pivotal role in discovering exoplanets, shedding light on the potential for life beyond our solar system and deepening our understanding of planetary formation. As technology advances, these cosmic sentinels continue to push the boundaries of our knowledge, unveiling the secrets of our vast and ancient universe. Particle accelerators serve as time machines, allowing scientists to peer into the distant past of our universe. These massive machines propel subatomic particles to incredibly high speeds and smash them together, recreating conditions that existed fractions of a second after the Big Bang. By studying these high-energy collisions, researchers can unravel the mysteries of how matter behaved in the universe's infancy. One of the primary goals of particle accelerators is to produce and study exotic particles that were abundant in the early universe but are rarely seen today. These include particles like the Higgs boson, which gives other particles their mass, and quark-gluon plasma, a state of matter that existed shortly after the Big Bang. By observing these particles and their interactions, scientists can test and refine their theories about the fundamental laws of physics that govern our universe. Particle accelerators also help researchers investigate the asymmetry between matter and antimatter in the early universe. According to our current understanding, equal amounts of matter and antimatter should have been created during the Big Bang. However, our universe is dominated by matter. By recreating the conditions of the early universe, scientists hope to uncover the processes that led to this imbalance. Furthermore, these powerful machines enable scientists to explore the nature of dark matter and dark energy, which make up a significant portion of our universe but remain poorly understood. By simulating the extreme conditions of the early cosmos, researchers can search for particles that might explain these mysterious components and help complete our picture of the universe's composition and evolution. Gravitational wave detectors offer us a unique window into some of the most energetic and violent events in the universe. These sophisticated instruments can detect ripples in the fabric of space-time caused by massive cosmic collisions, such as the merger of black holes or neutron stars. When these cataclysmic events occur, they send out waves of gravitational energy that travel across the cosmos at the speed of light. As these waves pass through Earth, they cause incredibly tiny distortions in space itself. Gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, known as LIGO, are designed to measure these minuscule changes, which are smaller than the width of an atomic nucleus. By analyzing the specific patterns of these waves, scientists can deduce a wealth of information about the cosmic events that produced them. They can determine the masses of the objects involved, their approximate location in the sky, and even how they were spinning before they collided. This data allows researchers to test theories about the formation and evolution of black holes, the properties of neutron stars, and the behavior of matter in extreme conditions. Perhaps most excitingly, gravitational wave detectors allow us to observe phenomena that are invisible to traditional telescopes. They can detect the mergers of black holes, which emit no light and provide insights into the earliest moments of our universe, long before the first stars began to shine. This new form of astronomy is revolutionizing our understanding of the cosmos, revealing a universe that is more dynamic and violent than we ever imagined. As we peer deeper into the cosmos, future technologies promise to revolutionize our understanding of the universe's origin. Advanced gravitational wave detectors will allow us to listen to the echoes of the Big Bang, providing unprecedented insights into the earliest moments of cosmic history. These detectors, far more sensitive than current versions, could potentially capture gravitational waves from the inflationary period, offering a window into the universe when it was less than a second old. Quantum computers represent another leap forward in our quest to unravel cosmic mysteries. These powerful machines could simulate complex quantum systems, helping us model the behavior of matter and energy under extreme conditions that existed in the early universe. This capability might bridge the gap between quantum mechanics and general relativity, potentially leading to a unified theory of everything. Space-based telescopes with capabilities far beyond our current technology will play a crucial role in advancing our knowledge. These next-generation observatories could detect the faint light of the first stars and galaxies, illuminating the cosmic dark ages that followed the Big Bang. By studying these ancient luminaries, we may gain vital clues about the formation and evolution of cosmic structures. Particle accelerators of the future, dwarfing even the Large Hadron Collider, could recreate conditions closer to those of the early universe. These machines might produce exotic particles that existed only in the intense heat and density following the Big Bang, helping us understand the fundamental forces and particles that shaped our cosmos. As these technologies converge, they promise to paint a clearer picture of our cosmic origins, answering long-standing questions and undoubtedly raising new ones in the process. Computer simulations have become invaluable tools in unraveling the mysteries of the early universe. These powerful digital models allow scientists to recreate and study cosmic events that occurred billions of years ago, far beyond the reach of direct observation. By inputting known physical laws and initial conditions, researchers can simulate the evolution of the universe from its earliest moments. These simulations track the behavior of matter and energy over vast scales of time and space, revealing how galaxies formed and how the cosmic web of structure we see today came into being. One of the most significant advantages of computer simulations is their ability to test different theories about the early universe. Scientists can adjust parameters and see how changes affect the outcome, comparing the results to actual observations of the cosmos. This process helps refine our understanding of fundamental concepts like dark matter, dark energy, and the inflationary period that occurred shortly after the Big Bang. Moreover, simulations enable scientists to make predictions about future observations and guide the development of new telescopes and experiments. As computing power continues to grow, these digital models become increasingly sophisticated, offering ever more detailed insights into the birth and evolution of our universe. Observing the earliest moments of the universe presents significant challenges for astronomers and cosmologists. The primary obstacle is the vast distance in both space and time. The light from these ancient events has traveled for billions of years to reach us, becoming incredibly faint and stretched by the expansion of the universe. Another major challenge is the cosmic microwave background radiation, which acts like a curtain, blocking our view of anything that happened before about 380,000 years after the Big Bang. This radiation was emitted when the universe cooled enough for atoms to form, making it transparent to light for the first time. The extreme conditions of the early universe also pose difficulties for our understanding. The laws of physics as we know them break down at the incredibly high energies and densities present in the first fractions of a second after the Big Bang. This limits our ability to model and predict what occurred during this period. Technological limitations further complicate our observations. Even our most advanced telescopes and detectors struggle to capture the faint signals from the early universe. Scientists are constantly developing new instruments and techniques to peer further back in time, but each advancement brings new challenges in data analysis and interpretation. Mathematics serves as a powerful tool in unraveling the mysteries of the universe's origin. It provides a framework for describing complex phenomena and making predictions about cosmic events that occurred billions of years ago. Through mathematical models, scientists can simulate the conditions present at the beginning of time, allowing us to explore scenarios that are impossible to recreate in a laboratory. One of the most significant applications of mathematics in understanding the universe's origin is in the study of the Big Bang theory. Equations derived from general relativity and quantum mechanics help scientists calculate the expansion rate of the universe, the formation of early cosmic structures, and the distribution of matter and energy in the moments following the Big Bang. Mathematical analysis of cosmic microwave background radiation, a faint glow left over from the early universe, has provided crucial evidence supporting our current understanding of cosmic origins. By applying statistical methods to this ancient light, researchers have been able to map the tiny fluctuations that eventually led to the formation of galaxies and large-scale structures we observe today. Furthermore, mathematics allows scientists to test and refine theories about the universe's beginning by comparing predictions with observational data. This iterative process of mathematical modeling and empirical verification has led to remarkable advancements in our understanding of cosmic inflation, dark matter, and the fundamental forces that shaped our universe in its earliest moments. The early universe, a period of intense activity and rapid change, is best described by several key mathematical models. The most prominent among these is the lambda cold dark matter model, often referred to as lambda CDM. This model combines the concept of dark energy, represented by the cosmological constant lambda, with the presence of cold dark matter. Another crucial model is the theory of cosmic inflation, proposed by physicist Alan Guth. This theory explains the rapid expansion of the universe in its earliest moments, solving several cosmological puzzles such as the horizon problem and the flatness problem. The Big Bang model, while not strictly mathematical, forms the foundation for our understanding of the early universe. It is supported by mathematical descriptions of nucleosynthesis, which explain the formation of light elements in the first few minutes after the Big Bang. Quantum field theory also plays a vital role in describing the behavior of particles and forces in the extreme conditions of the early universe. These models, working together, help scientists paint a comprehensive picture of our cosmic origins, from the first fractions of a second to the formation of the first stars and galaxies. The concept of infinity plays a crucial role in our understanding of the universe's origin, challenging our perceptions and pushing the boundaries of scientific inquiry. In cosmology, infinity arises in various models, attempting to explain how our universe began and what might have existed before the Big Bang. One prominent theory suggests that our universe emerged from an infinitely dense and hot singularity. This singularity, a point of infinite density and zero volume, represents a breakdown in our current understanding of physics. The laws that govern our universe as we know it cease to function at this extreme, leaving scientists grappling with the implications of infinity at the very moment of creation. Some models propose an eternal or cyclical universe, where our Big Bang is just one of infinitely many cosmic events. In these scenarios, the universe expands, contracts, and rebounds in an endless cycle, with no true beginning or end. This concept of infinity extends not just to space, but to time itself, challenging our notions of causality and the nature of existence. Other theories explore the possibility of infinite parallel universes, or a multiverse. These models suggest that our universe is just one of countless others, each with its own laws of physics and potential for life. The multiverse concept introduces the idea of infinite possibilities and variations, expanding our understanding of reality beyond the confines of our observable universe. Differential equations are fundamental tools in cosmology, allowing scientists to model and understand the complex dynamics of the universe. These mathematical expressions describe how various cosmic quantities change in relation to one another, providing a framework to explore the evolution of the cosmos over time. In cosmology, differential equations are crucial for describing the expansion of the universe. The Friedmann equations, derived from Einstein's field equations in general relativity, use differential equations to relate the scale factor of the universe to its energy content. This enables cosmologists to model how the universe expands or contracts under different conditions. Differential equations also play a vital role in understanding the formation and evolution of cosmic structures. They help describe how matter clumps together under the influence of gravity, leading to the formation of galaxies and galaxy clusters. These equations allow scientists to model the growth of density fluctuations in the early universe, which eventually gave rise to the cosmic web we observe today. Furthermore, differential equations are essential in studying the physics of stars and other celestial bodies. They describe stellar evolution, including processes like nuclear fusion and energy transfer within stars. By solving these equations, astronomers can predict the life cycles of stars and understand phenomena such as supernovae and black hole formation. Geometry plays a crucial role in unraveling the mysteries of the universe's structure. It provides a framework for describing and analyzing the shape and layout of cosmic objects and the space between them. From the curves of planetary orbits to the vast cosmic web of galaxy clusters, geometric principles help scientists model and predict the behavior of celestial bodies. One of the most significant contributions of geometry to our understanding of the cosmos comes from Einstein's theory of general relativity. This groundbreaking idea describes gravity as a geometric property of space and time rather than a force. It explains how massive objects warp the fabric of space-time, creating what we perceive as gravitational effects. This geometric approach has led to predictions and observations of phenomena like gravitational lensing, where light bends around massive objects, distorting our view of distant galaxies. Geometry also helps us comprehend the overall shape of the universe. Cosmologists use concepts from non-Euclidean geometry to explore whether the universe is flat, curved, or has a more complex topology. These geometric models inform our understanding of the universe's past and potential future, including theories about its origin and ultimate fate. Furthermore, geometric analysis of cosmic microwave background radiation has revealed crucial information about the early universe. The patterns and distributions observed in this ancient light provide insights into the universe's composition, age, and evolution, all interpreted through the lens of geometry. As we continue to explore the cosmos, geometry remains an indispensable tool for decoding the fundamental nature of our universe. Quantum fluctuations are a fundamental aspect of our universe, occurring at the smallest scales of reality. To understand these fleeting events, scientists rely on several key mathematical concepts. Probability theory forms the backbone of quantum mechanics, allowing us to describe the likelihood of particles appearing and disappearing in the quantum foam. This probabilistic approach is essential because quantum fluctuations are inherently unpredictable, yet follow statistical patterns. Complex numbers play a crucial role in quantum calculations. These numbers, which include both real and imaginary components, are used to represent quantum states and the wave functions of particles. They allow physicists to model the behavior of quantum systems with remarkable accuracy. Differential equations are another vital tool for describing quantum fluctuations. These mathematical expressions help scientists model how quantum systems change over time, capturing the dynamic nature of particles popping in and out of existence. Lastly, linear algebra provides the framework for understanding quantum superposition and entanglement. This branch of mathematics deals with vector spaces and linear transformations, which are essential for describing the multiple states a quantum system can exist in simultaneously. Mathematical abstractions play a crucial role in our understanding of the cosmos, serving as powerful tools to describe and predict the behavior of physical reality. In cosmology, these abstractions allow scientists to model complex phenomena that are often beyond direct observation or intuition. For instance, the equations of general relativity, developed by Albert Einstein, provide a mathematical framework to describe the curvature of spacetime and the effects of gravity on a cosmic scale. These equations have led to predictions of phenomena like black holes and gravitational waves, which were later confirmed through observations. Similarly, quantum mechanics uses abstract mathematical concepts to describe the behavior of particles at the smallest scales. This seemingly counterintuitive framework has proven remarkably accurate in explaining phenomena like the behavior of subatomic particles and the nature of fundamental forces. The success of these mathematical models in predicting and explaining observed phenomena demonstrates their deep connection to physical reality. However, it is important to note that while mathematics provides an excellent approximation of reality, it may not always capture the full complexity of the universe. Ongoing research continues to refine and expand these models, pushing the boundaries of our understanding of the cosmos. The origin of our universe remains one of the most profound mysteries in science. Cosmologists grapple with several fundamental questions that continue to elude definitive answers. One of the most pressing enigmas is what existed before the Big Bang. Our current understanding of physics breaks down when we attempt to probe the earliest moments of the universe, leaving us unable to peer beyond this cosmic curtain. Scientists debate whether there was a prior state, a multiverse, or if the concept of before even applies to the birth of space and time. Another major puzzle is the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. While we can observe its effects, we have yet to understand its fundamental properties or origin. This invisible energy, which makes up about 68% of the universe, challenges our grasp of fundamental physics. The question of why there is more matter than antimatter in the universe also perplexes researchers. According to our current models, equal amounts of matter and antimatter should have been created in the Big Bang, yet our universe is dominated by matter. Understanding this asymmetry could reveal crucial insights into the laws governing the cosmos and its earliest moments. Dark matter remains one of the most enigmatic components of our universe, and its true nature could revolutionize our understanding of cosmic origins. This invisible substance, which does not interact with light or other forms of electromagnetic radiation, is believed to make up about 85% of all matter in the universe. Its gravitational effects are observed in the rotation of galaxies and the movement of galaxy clusters, yet its composition remains a mystery. If dark matter consists of weakly interacting massive particles, as many scientists theorize, it would have played a crucial role in the formation of the first structures in the early universe. These particles could have clumped together under their own gravity, creating the scaffolding upon which ordinary matter later collected to form galaxies and galaxy clusters. This scenario would explain the large-scale structure we observe in the cosmos today. However, if dark matter turns out to be composed of ultralight particles or even primordial black holes, it would dramatically alter our models of how the universe evolved. Such discoveries could lead to new insights into the conditions present during the Big Bang and the subsequent expansion of the universe. They might also shed light on the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. Unraveling the secrets of dark matter could potentially bridge the gap between quantum mechanics and general relativity, leading to a more complete theory of the fundamental forces that shaped our universe from its earliest moments. As we continue to probe the nature of dark matter, we may find ourselves rewriting the cosmic story of our origins. The cosmological constant problem stands as one of the most perplexing challenges in modern physics, bridging the gap between quantum mechanics and general relativity. At its core, this issue arises from the vast discrepancy between theoretical predictions and observational evidence regarding the energy density of empty space. Quantum field theory suggests that empty space should be teeming with virtual particles popping in and out of existence, contributing to an enormous amount of energy. This theoretical energy density is so large that it should cause the universe to expand at an incredible rate or even tear itself apart. However, astronomical observations reveal a universe that is expanding much more slowly, indicating a much smaller energy density of empty space. This enormous mismatch between theory and observation, spanning over 100 orders of magnitude, has profound implications for our understanding of the universe. It challenges our current models of particle physics and cosmology, suggesting that there might be fundamental aspects of reality that we have yet to grasp. The cosmological constant problem also intersects with the concept of dark energy, the mysterious force driving the accelerated expansion of the universe. Solving this puzzle could potentially revolutionize our understanding of the cosmos, shedding light on the nature of vacuum energy, the fate of the universe, and the fundamental laws that govern reality at both quantum and cosmic scales. The matter-antimatter asymmetry problem is a fundamental puzzle that connects directly to the earliest moments of our universe. In the first fractions of a second after the Big Bang, theory suggests that equal amounts of matter and antimatter should have been created. However, the universe we observe today is dominated by matter, with antimatter being exceedingly rare. This imbalance poses a significant challenge to our understanding of the early universe. If matter and antimatter had been produced in exactly equal quantities, they should have annihilated each other completely, leaving behind a universe filled only with radiation. Yet, we exist in a matter-dominated universe, surrounded by galaxies, stars, and planets composed of matter. Scientists propose that some unknown process in the extremely hot and dense conditions of the early universe must have slightly favored the production of matter over antimatter. This tiny imbalance, perhaps as small as one extra particle of matter for every 10 billion pairs of particles and antiparticles, would have been enough to seed the universe we see today, after most of the matter and antimatter annihilated. Understanding this asymmetry is crucial for explaining our very existence and unraveling the mysteries of the universe's earliest moments. It pushes researchers to explore new physics beyond the standard model, searching for mechanisms that could have produced this matter-antimatter imbalance in the primordial cosmos. The horizon problem is a perplexing cosmological issue that challenges our understanding of the early universe. It arises from the observation that distant regions of space, which should have never been in contact with each other, appear to have nearly identical properties, such as temperature and density. According to our current models of the universe's expansion, light and other forms of information could not have traveled between these far-flung regions since the Big Bang. Yet, when we look at the cosmic microwave background radiation, the afterglow of the early universe, we see a remarkably uniform temperature across the entire sky. This uniformity suggests that these regions must have been in thermal equilibrium at some point in the past, which seems impossible given the vast distances between them and the limited time since the Big Bang. The horizon problem forces us to question our assumptions about the early universe and how information could have been exchanged across such enormous distances. To address this conundrum, scientists have proposed various solutions, including the theory of cosmic inflation. This theory suggests that the universe underwent a brief period of exponential expansion in its earliest moments, allowing previously connected regions to be stretched far apart. While inflation provides a potential explanation, the horizon problem continues to drive research and debate in cosmology, reminding us of the mysteries that still lurk in our understanding of the universe's origins and evolution. The flatness problem challenges our understanding of the early universe and its evolution. Observations show that the universe's geometry is remarkably close to flat, with a curvature so small it's barely detectable. This near-perfect flatness presents a significant puzzle for cosmologists. In the standard Big Bang model, even a tiny deviation from flatness in the early universe should have rapidly grown over time, resulting in a universe that is either highly curved or rapidly expanding. However, we observe neither of these outcomes. Instead, the universe appears to have maintained its flatness with extraordinary precision over billions of years. This discrepancy between theoretical predictions and observational evidence suggests that our models of the early universe may be incomplete. It implies that some mechanism must have existed to drive the universe towards flatness in its earliest moments. The inflationary theory, which proposes a brief period of exponential expansion in the first fraction of a second after the Big Bang, offers one potential solution to this problem. The flatness problem has thus spurred the development of new cosmological theories and continues to shape our understanding of the universe's beginning. It underscores the need for a more comprehensive model that can explain the universe's observed properties without requiring such precise initial conditions. To fully explain the origin of the universe, scientists may need to develop new physics that goes beyond our current understanding. One key area is reconciling quantum mechanics with general relativity, as these two fundamental theories break down when describing the extreme conditions of the early universe. This unified theory, often called quantum gravity, could provide insights into the first moments after the Big Bang. Another crucial aspect is understanding the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. New physics might be needed to explain its properties and how it relates to the vacuum energy of space. Similarly, dark matter, which makes up a significant portion of the universe's mass, remains elusive. Uncovering its true nature could require extensions to the standard model of particle physics. The concept of cosmic inflation, which describes an incredibly rapid expansion of space in the universe's first fraction of a second, also presents challenges. While inflation explains many observed features of the cosmos, the underlying mechanism and the transition to the current phase of expansion are not fully understood. New theoretical frameworks might be necessary to explain these processes. Lastly, the question of what came before the Big Bang, if anything, remains a profound mystery. Addressing this may require entirely new concepts and mathematical tools, potentially involving multiple universes or higher dimensions. These new physics theories could revolutionize our understanding of the universe's origins and fundamental nature.